Jai.
I wish and hope everyone has joined the link successfully. All the delegates are already with us. So, shall we start?
Yes, Nano sir, you start.
Okay. Honorable dignitaries, respected teachers, young researchers, and beloved students, a very good morning to one and all. Myself, Dr. Nadargi, feels privileged to welcome you all on behalf of Organizing Committee of National E-Conference on Materials for Emerging Technologies 2021, organized by School of Physical Sciences and IQSC of Punyashlok Ahilyadevi Holkar, Sholapur University, Sholapur. Well, Albert Einstein said if we knew what it was we were doing, it would not be called as a research. With this line, I would like to say this is an occasion where we get an opportunity to test our knowledge and understanding. It is the time where we get an exposure about what the best of the brain thinks. So to start the research feast, I would like to request the convener of the conference and director, School of Physical Sciences and IQSC, Professor V.B. Patil sir, to give the introduction of the conference. And I also request Professor Patil sir to introduce the chief guest of inaugural function, respected Dr. D.K. Aswal sir, to all of us. Please, Professor Patil sir. Over to Patil
Namaskar. Namaskar. Good morning. Honorable Dr. Mulani Padanvis Madam, Vice Chancellor, Punyashlok Ahilyadevi Holkar, Solapur University, Chief Guest of this National E-Conference, Professor Dr. D.K. Aswal sir, Director, National Physical Laboratory, New Delhi, Keynote Speaker, Professor P.S. Patil, Pro Vice Chancellor, Shivaji University, Kolhapur, Dr. Devendranath Mishra, Pro Vice Chancellor, Punyashlok Ahilyadevi Holkar, Solapur University, Solapur, Professor V.B. Kuthe, in charge, Registrar and Director, School of Computational Sciences, PH, Solapur University, directors from the various schools on the campus, heads, faculty members, and organizing team of MET-21 and participant friends. At the outset, on behalf of Punyashlok Ahilyadevi Holkar, Solapur University, I heartily welcome all. The National E-Conference on Materials for Emerging Technologies is jointly organized by School of Physical Sciences and Internal Quality Assurance Cell of PH Solapur University. The primary objective of the E-Conference are to provide academicians, scientists, researchers, and PG students with a forum to create opportunities for the next generation workforce in the allied fields of material science for the emerging technologies. Also to meet eminent researchers and inspiring experts from the field to discuss ground advances, recent innovations, and implementations of materials in various domains. The conference will cover broad areas of the topic related to materials for emerging technologies in the field of supercapacitors, batteries, gas sensors, solar cells, materials for smart sensor, photocatalysis, etc. For the conference, Professor P.S. Patil, Pro Vice Chancellor, Solapur, Kolhapur, Dr. Shashwati Sen, Scientific Officer, Technical Physics Division, BIRC Mumbai, and Professor B.R. Sangpa, VNIT Nagpur, will participate as a keynote speaker and a resource person, and will explore their views on materials and recent energy technologies. For this national e-conference, it is really a great pleasure to have a chief guest, Professor D.K. Aswal sir, and Honorable Vice Chancellor, Dr. Mulani Padanvis Madam, as a president. I'm glad to tell you that for this national e-conference, 321 participants, that is the PG students, PhD research scholars, and faculty members participated from various parts of the India. The live streaming of the conference is broadcasted through the Zoom Cloud meeting and the IQSC YouTube channel. It gives me an immense pleasure to introduce you the chief guest of today's conference and my mentor, Professor Dr. D.K. Aswal sir, Director CSR National Physics Laboratory, NPL, New Delhi. Though he doesn't need an introduction to the scientific community, as a matter of formality, I would like to briefly introduce you. Sir has taken over the charge of Director CSR, National Physical Laboratory, CSR NPL New Delhi, with effect from 15th December 2015, maintaining lean with its position as an outstanding scientist at Baba Atomic Research Center, BRC, Department of Atomic Energy, Government of India, Mumbai. During 2012-2015, Dr. Aswal sir has also served as Secretary, Atomic Energy Education Society, Mumbai. Dr. Aswal sir joined BRC through the training school 30th batch of the year 1986 after completing MSc Physics, gold medalist, from the Garhwal University in 1985. He obtained PhD in Physics from Mumbai University and subsequently carried out postdoctoral research work at Research Institute of Electronics, Hamamatsu, Japan. He is a condensed matter physicist of international repute and has made several outstanding contributions in the areas of molecular electronics, physics of organic fields and their applications, thermoelectric power generators, and gas sensors. He has edited many books, contributed a number of journal papers, filed 3 patents, and secured the trademark of Bharatiya Nirdeshak Dravyas, that is called as BND, the Indian Certified Research Reference Material. As the director of CSR NPL, he has launched several national programs. As the president of Meteorological Society of India, MSI New Delhi, and chairman, as well as the member of various national committees, Dr. Aswal sir ensures that the national policies, academia, strategic sectors, and industries are benefited from the quality infrastructure of the country. As a member of International Bureau of Weights and Measures, that is BIPM, France, Asia Pacific Meteorology Program, APMP, and International Union of Pure and Applied Physics, that is IUPAP, he ensures that the country interests at international level are fulfilled. His current focus is to enhance the meteorological capabilities of India at par with international standards for continuous improvement of the quality and safety of life in the country and making CSR NPL as a growth engine of our nation. It is our great pleasure that Dr. Aswal sir has accepted our invitation to be a chief guest and inaugurate the conference from his busy schedule. Thank you very much, sir. Once again, from the Punishluka Valedictory Holkar, Solapur University, for accepting the invitation for this National E-Conference. Thank you, sir. Over to Nadargi.
Thank you, sir. Thank you for such a nice introduction. Now let us have the pleasure of listening to our chief guest, Dr. D.K. Aswal, sir. Over to Aswal, sir, please.
Yeah, so can you allow me to share my slides?
Yes, sir.
Yes, sir.
So,
Just a second.
respected Vice Chancellor, Mrinali Pranajji, Vikas Patil, and other delegates, those who are attending this e-conference. Dr. Vikas Patil is known to me for a long time, and I am indeed very happy that he has made a immense contribution while staying at Solapur University. Many of his students, they have got the international recognition. He continues to collaborate with BRC, and this conference is very important. And just can you give me the access to for sharing?
Sir, access is given, sir.
Not yet. Okay. So today I am going to talk. I give a brief overview of the so-called Aswal model of inclusive growth. Now, inclusive growth is defined by the Organization for Economic Cooperation and Development, that is called OECD. And that means that the economic growth that is distributed fairly across society and creates opportunities for all. So whatever research we do in the university system, whatever research we do in the R&D centers, until and unless the economy of the country is not improved, we are not going to do justice with the science. The science and technology is good enough for creation of the knowledge. It is good for our publications. It is good for our promotions. It is good for our recognition. We get award. Probably it is good for holding our positions. But if this knowledge is not converted into the wealth, the country will always remain the weak and the poor. And that is the essentially a small model, how to do it. Now, since this is the material conference, and the slide I have taken from the internet, which shows that the top 10 material industry trends in 2021 are the followings. And there are many, many startups. They have come up. So one is the sustainability. You see, we construct our house, and then once the house becomes old, we throw all the materials anywhere. When you use the plastic, we throw the plastic anywhere. It means that the materials do not have the sustainability. It has to be a closed cycle loop. So that kind of research that need to be done. Smart materials. Now, human being cannot do each and everything. So we need the smart materials for pressure, for sensors, all the comes under the smart. Nanotechnology, everybody talks about the nanotechnology. Everybody knows it. Additive manufacturing, lightweighting. Now, can we make the very tough material and hard material with the good properties, but very, very lightweight so that energy consumption is low? Material informatics, everything, everybody is having the knowledge now, and all the knowledge that need to be stored, the memory devices, can you make the materials which are informatics? Advanced composites, again, for lightweighting and additive manufacturing. Graphene and 2D materials, that also falls under the category of nanotechnology. Surface engineering, particularly with corona virus, the bio problems of the viruses is a key. So can we have the surfaces where the virus does not attach at all? No, that can be one of the problems. And materials management, that is a very, very important as we are going for the industry 4.0. So if you look at the key important areas for material research, is the sustainability. The material which you are using, they should not end up another kind of problem to us. Nanotechnology is 12%, lightweighting 10%, materials information 10%. Response smart material 12%, additive manufacturing 10%, advanced composites, graphene, So these are the things which the world is looking forward at this point of time. And there are many, many startups they have formed up. So if you look at the Europe and America are the two large big countries where this is taking up. In India, you can see in the map that there are many startups coming up. But are we really converting these startups into real products? So that need to be looked into it. Now, this is a very recent study which has come up that India is the number 3 in number of publications in nanotechnology. China publishes 74,000 papers, USA 23,000 papers, India 15,000 papers. And therefore, many times we start patting ourselves. India to bahut acha kaam kar raha hai. We are third in the worldwide. But look, hold on. Is that good enough? Now look the patents in the nanotechnology. China 825, USA 4,666, India only 54. And if you look at the share, the 45% of the share in nanotechnology in patents goes to America, followed by South Korea, Japan, and India has got 0.52% only. It means what? We have created a knowledge, we have published and bound them in the journals, and then we are not worried about it. Sorry, we have to patent, we have to preserve our IP. We have to convert them in a product and launch in the market. That is going to give you the wealth. So my initial statement, if you want to go economically, we have to look into the, not only in publications, but also in the patenting, but also in the startups, but also into the making the product, but also looking for the sustainability. So this is not only which I am saying, this is the United Nations keeps on telling all the time that we have what is sustainable development goals. We should have no poverty, we should have no hunger, we should have good health, quality education. But if you see our country, we have got 1.4 billion people. The way of life is entirely different. There are very poor people, they do not have enough food, they do not have the good housing, quality education. There's so many problems are there. And that is essentially because the economy is not as strong as we should expect it. So when I was looking into that, where we are making error, so essentially the modern time is to create the knowledge. The economy is the knowledge-based economy. It means we have to produce the knowledge. How do we produce the knowledge? So there are many, many models. One of the earliest model is the mode 1 model, where you do the linear research. Linear research means you sit in the laboratory, read the library, get literature done, get some equipment done, do some research, do incremental research, publish as a paper. And then it is from library to library. We got a problem from library and we pack that knowledge into the library. Then mode 2 model came, and that is called the context-driven research. It means you go to the industry and ask what is the problem of industry and solve that problem. That's called mode 2. Now the mode 2 again has a problem that you do not create a new knowledge. You do what the industry is asking. And there's subsequently the third model came, which is known as the mode 3 of knowledge production, which is a mix of two. You have to do fundamental research as well as you have to do the context-driven research. But then all the ball game was between the academia and the industry. So government pitched in. Look, we need to convert this knowledge into the wealth, and therefore the triple helix model came. Everybody knows the triple helix model, where the academia and industry is supported by the government. How government does it? Government pumps the money. All the education institution, all the R&D laboratories in any of the country in the world is due to this triple helix model. Otherwise, the R&D institution would not sustain. Now, the interfacing between academia and industry, the funding alone is not good enough. Then they started doing the publication, they started asking you to do for patent, they started doing for the startup, incubation center. So these are the strategies which are going on. But are the scientists really geared up to take up the startups and make the final products? When you ask any of the scientists, they say this is not our business. Our job is to only do R&D. So, but that is not enough, because a huge amount of money is spent by the government on us. Then came the quadruple model in which whatever work we are doing, that is being done for the society. Now, if society is not benefited, then there is a problem. So therefore, the quadruple helix model came: government, academia, industry, and society. But the developed nations are very smart. They throw these models, but hardly anybody tells you how the government, academia, industry, and society should work together. Where are the problems? What is the gelling force? Because as an academician, I will always say that government is not funding as well. Industry will say that the technology made by university is very poor or academia is very poor, they are not using it. We'll say that industry is not taking a problem. We keep on blaming each other. So looking at that one, the ASWAL model came into existence. And based on that book, we have written a book to commemorate the 75th Foundation Day. That is the ASWAL model of inclusive growth. And the book title is that Methodology for Inclusive Growth of India. Now, in this case, the government, academia, industry, and society, they will gel together only when we all have the same measurements. And that's why I call it methodology-driven quality infrastructure as a binding force. So as you know that the government has got its own responsibility to make policies, regulation, financing. Academia has got its role on the education, research development, incubators, and spin-off. Industry has got the products and this one, and society has got its own role, and including the media, civil society. The biggest problem, what I see, is that all of us has a different measurements. And when you have a different measurement, we are not bound together. So high economy and high quality can come up only when all have got the accurate and precise measurements in each of the domain. And as you know that the SI units of measurement, the 7 SI units, mole, candela, kilogram, meter, second, ampere, and Kelvin, they are the ultimate gods of the measurement. They have got a zero uncertainty. Remaining will have all the uncertainties. And the whole idea is that if we can minimize our measurement uncertainty, come close to the SI unit, all of us will have the same measurements, and therefore there won't be any biasing towards anyone. I will highlight that a little in detail. So what is the quality infrastructure? Quality infrastructure is the scientific term coined by United Nations Industrial Development Organization. And it has got three organized components. One is the metrology, that is the science of measurement. There's an international body called the International Bureau of Weights and Measure. In Asia, it is the Asia Pacific Metrology Program. And as a director of NPL, which is the National Metrology Institute of India, I represent both of them. And BRC, Bhabha Atomic Center, which is my parental organization, is the designated institute for the ionization radiation. Rest of the measurements are done by the National Physical Laboratory. Now, when we do research, when we do a product, we have to have a written standard. So NPL and BRC are meant for the measurement standards, which are traceable to SI units. When we work upon that, we have our standards. So written standards are made internationally by ISO, International Organization Standards, Electrotechnical Committee, and World Standards Service Network. And in India, it is the Bureau of Indian Standards. Now, none of us, majority of us, do not contribute to the formulation of the neither the measurement standard nor the Indian standards. Now, without these two standards, measurement and standards and written standards, it is very difficult to formulate a technology. And are we doing fine? So there is called accreditation, and that's a very, very important. It is a third-party evaluation. Any scientist who makes a product, he says that is perfect. There's no problem with it. But when he gives to industry, industry says it's the fault. So who evaluates them? So there is a called accreditation. That is a third-party evaluation. Now, once we have got these three in place, and scientific people work as per the accurate measurement, as per written standards, as per the third-party evaluation by the accreditation, which is NABL in India, there will be a conformity assessment. Conformity assessment, whatever I measured, whatever I said, is equal to anybody in the world can measure that value. And if that is done, there is no margin of errors. And when there is no margin of error, everybody is going to be benefited. And that is what essentially is the theme of the SWAL model. So as you know that unification of measurements was done in 1875 in France, and therefore the BIPM became. And this BIPM is the agency that defines the 7 SI standards. And in India, as per the government gazette, National Physical Laboratory is the custodian of all the measurement standards. And I was fortunate to redefine the SI units and vote on behalf of Government of India for the redefinition of the SI units. Now, what has happened is that these SI units are 7 in numbers, kilogram, meter, second, ampere, Kelvin, candela, and now they are associated with the fundamental constants of the nature. It means now these SI units are not only valid for on this planet, but they are also valid for any of the planet in the universe. Because when you talk about kilogram, it's not kilogram now. It is the number of Planck constant. So number of Planck constants in Earth and in Moon, in Mars, they is going to be the same. And therefore we can communicate, not only in this Earth, we can communicate to the universe. And that is a big, big change that has occurred in 2019. Say, for example, in schools, when we do the G measurements, you know, I know that I could never get the 9.8 G value. And I have asked one of the schools to conduct this G as experiment. Instead of 9.8, they got 15, 16, 21, 22. But if you do that and give a report to your teacher, teacher is going to give you a 0 mark. Because they say that you do not know the value is 9.8. But teacher does not teach us how to get that 9.8 value. It's a very tough task to get a 9.8 using a pendulum. And at NPL, we have done some experiment. And then we realized that 9.8 is getting a very, because the pendulum should not swing more than 10 degrees. And there are many sources of errors which comes in this one. The accuracy and precision. The timing should be measured with the benchmark of atomic clocks, reaction time of experimenter, statistical errors, mass distribution of your pendulum, air buoyancy, sting stretching, and you have to get the uncertainty in your measurement using these parameters. And once we do that, you can get the 9.8 plus minus 0.1 meter per second square. But that is really a heavy task. But unfortunately, in school days, we either reverse calculate or we manipulate data and we get 10 out of 10 marks or 20 or 20 marks, but without getting the correct value. And that culture for science is really bad. So we should be giving marks those who get value of 12, 18, 16, but then we should also ask that what are your sources of error and how to minimize it that. So the scientific temperament goes up. So therefore the measurement is so key important to it. So many times we ask that the measurement should be very accurate and precise. Precise is the reproducibility. Accurate, we say that it should be close to the true value. Now, when we ask the scientist what is the true value, how do you calculate the true value? To my knowledge, majority of us do not understand how to get the true value. Now, once we do not know the true value in your measurement, then how we get the accurate value? Because accurate value is nothing but how close you are to the true value. So one has to understand that measurement definition. And when we do measurement, say for example, if the first one is the in control. So irrespective of time, it should have the same value. But often we get the bias, we get the step change, we get the drift, and we get the uncertainty. And when you get a large uncertainty, as we show in this value, when there's a large uncertainty increasing, we can get a false positive and false negative values. And therefore, many times you might have seen that if we go for a sugar testing of our blood sample, since the uncertainty is large, so they will make a false positive. You are not a sugar patient, but you will be made a sugar patient. And this is a phenomenon in India. Since our measurements are not accurate, and therefore the false positive and false negative are huge, and therefore the expenditure on health is large. It is not only health, it is all sectors. So for that, we need to understand the measurement. When we have a measuring instrument, let us when a scale, is 30 centimeter scale. If there are 5 manufacturers of the small scale, or one ruler, 1 feet scale, you match them, they will never fit to 30 centimeters. There will be a difference. Now, out of 5, if I want to know which is the correct scale, this answer cannot be given by many of the even leading experts, because we do not understand what measurement is. So basically, the measuring instrument should be calibrated working the standard, working to the reference standard, reference to the secondary standard, reference primary standard, and finally the SI unit. The pyramid shows that the uncertainty measurement is increasing, and SI unit only has the zero uncertainty. So we have to measure with respect to zero uncertainty. So real definition of measurement is that each measurement has to demonstrate unbroken traceability chain to a national primary standard and a calculation of measurement uncertainty for each transfer in the chain. And if they are missing, then your measurement is just indicative. You have done some experiment. Like I have asked that we have done some G measurement, and that will be not acceptable if there is a legal problem at the international stage. And there are many examples which I can quote, but I will skip that. Or otherwise, we should have certified reference material. They are certified by the National Measurement Institute. So what I'm trying to say that even nut and bolt in this country, very rarely they match well. Why? Because the nut and bolt are made using the 2 different scales. They would be same if everything is with respect to this BIPM scale. So BIPM gives the scale to the NMI, this NPL. We give it to regional reference laboratory. And in India, we have about 1,600 weights and measure laboratories across the country. And many of the scientists, we do not know. Even in Solapur, there will be a controller of weights and measure. But I'm sure that you are not even aware of that. There is a weights and control of weights and measure in your one, and who will give you the correct measurements. Similarly, the weight, similarly the time, similarly is the ampere candela. All 7 SI units are transmitted like this. So whatever measurement we do, eventually they will end up in the 7 SI unit. So on 4th of January, when we celebrated our 75th Foundation Day, Honorable Prime Minister was very happy, and please do listen his speech on the YouTube available at our NPL website. He said that the metrology is the pillar for quality and credibility of India, and if you want to develop the brand India product. And on that day, we dedicated National Time and Bharatiya Nirishak Dravyas to the country. Also, the Bharatiya Nirishak Dravya, which is the Indian Certified Reference Material, the program which I initiated in 2017, and now we have got more than 101 in the market, and many of them are even being exported. We also had Indian Standard Time, the 4th best time in the world of 2.8 nanosecond. and this book, which was released by Honorable Minister, the Methodology for Inclusive Growth of India. So now this Aswal model, just trying to understand, when we do research in material science, like Solapur University are doing, we are making gas sensors. But are our gas sensors are in the market? When we want to install in a city, when we want to install at a home, when we install this one, eventually we are buying from the China. So where is this gap? So technology development and industrialization is a very, very key issue. Government for last 7 years have been making the huge campaign of Make in India and Made in India, that is Atmanirbhar Bharat. And very few of us have made a critical analysis of it. Of course, we need the investment. We need technologies, technology either imported or homegrown. If it is imported technology, we need innovation, because those technology which come from outside may not be applicable in India because of our weather conditions. So we need to do innovation. Then quality infrastructure. When we get those technology from outside, are we able to see that the technology which is coming in India is correct or not? So until unless we have got our measurement done correctly, we will not say the technology is good or bad. And finally, the skill development. Are we scientists know how to do the measurements? The measurement is the first requirement for the skill development. So sorry, many times we may be a scientist, very good scientist, but we are not skilled. We are not skilled to do the correct measurements. And when we do not do the correct measurement, any science coming out of this measurement is not correct. And therefore, the emphasis nationwide should be built upon that. We talk about Industry 1.0, mechanization. We talk about Industry 2.0, mass production. We took Industry 3.0, but India could not make a big dent. We could not succeed. And one of the reasons for that is that we didn't have our own quality infrastructure or measurement structure in the country. Now, this slide can be a little disturbing to us. And this also gives a mirror to us. This is taken from the United Nations Industrial Development Organization, where we talk about the manufacturing value added. It means any product that is made in India, how much money we earn out of it. And look the bottom curve, India. It is only $315 per capita per year. Very less. $300 means roughly 21,000 a year. Look, China, $3,000. UK, $4,000. USA, roughly 7,000. Japan, 8,000. Germany, close to $9,000. It means what? From your materials to the final product, everywhere you have got your contribution. And that's why you can increase the MBA. In India, most of things are imported. When we do science, equipments are imported, chemicals are imported. So our contribution is almost negligible. So that if the Make in India and Made in India, Atmanirbhar Bharat need to be successful, we need to enhance this MBA. And if you want to enhance the MBA, from concept to development to the manufacturing, the trading, that everything has to be done in India. But academia, we are happy that we made a model and we are happy with that. Industry, they want a ready-made product to be sold in the market. Then who is going to do this development and manufacturing in this country? And therefore, this bridging is important. And that's why the Aswal model is so important. And one of the things which I found the difference between the academia and industry, that our measurements are not same. And that's why when you talk about the technology readiness level from 1 to 9, everybody should have the same methodology. Everybody should have the same measurements. Everybody should have Indian standards. Everybody should be accredited by the NABL. But is that happening? That's not happening. Even we are not even aware of that. This should happen. So until that happens, we'll remain in our silos and we'll say that, okay, we have done a good job, and this everybody say that we have done a good job. But that is not going to serve us. So the quality infrastructure is very important to make a bridge between the national laboratories, universities, and the industries and MSMEs. For your cyber physical system, the time is very important. And NPL has now generated 2.8 nanosecond accurate time. That is one of the best in the world. Now we have started giving to the ISRO, and it has got huge economic impact. The time we give it to ISRO has allowed us to make our own GPS, has allowed us to give a much better imaging of our footprint. The power grid, when Honorable Prime Minister asked that on certain date at 9 p.m. for 9 minutes, we'll be shutting down the entire power system. Many people said that when everybody shuts the power, the grid will be overpowered and it will burn out. But it is because of the Indian National Time given to Power Grid Corporation, we made a smart grid. It means when the power was off at the houses, the production at the plant automatically gone down. And therefore, we avoided the breakdown of the power grid. Similarly, it is for cybersecurity, stock exchange, telecommunication, transport, everywhere. And one need time from the microsecond to the nanosecond. And we have done an analysis of this one. If all the computers, all the devices in this country are synchronized to NPL time, the country's GDP will grow automatically by 10%. So I already told the GPS, they see the GPS, the requirement for the 65 nanosecond for the 5G. And if you have to have a 5G in this country, which is very effective, the 65 nanosecond accuracy time is required. But fortunately, since NPL has got a capability of 2.8 nanosecond, we are ready to give this kind of facility to the entire India. And we are giving indeed. Similarly, is for the digital SI unit, which is emerging at the international level, but Indians are still not aware of data security, data format, data availability framework. Everywhere you require the digital SI. And that will be implemented in next 2 to 3 years if Industry 4.0 has to become one. Healthcare, it is so pity that this small incubator where the newborn baby is kept, which has got only 2 parameters, humidity and temperature. Even they are not well. So newborn baby die because the temperature outside shows 25 and inside is 40 degrees Celsius. Or the humidity inside is almost 100%, where there is hardly any place for the breathing for the newborn baby. So that need to be looked into that. So therefore, under National Health Policy, we have introduced that the metrology should be ingredient part of it. And we have been successful. And now the government of India has listed these 37 essential equipment for human welfare. And at NPL, we have started setting up the primary standard for these medical devices. One of them is the defibrillator, which we have done in 2018. Defibrillator is a device when the patient is at the deathbed. We give the patient a shock. And shock is nothing but an energy pulse. Energy pulse is given by energy divided by time. So roughly 100 millijoule for 10 millisecond. Now, if this 10 millisecond becomes, let us say, 5 millisecond, it means the energy dose is doubled. And the moment the doctor gives this to the heart will burst out. And there are many cases when a doctor applies this one, patient immediately dies. And his patient's relatives are seeing from outside. And then they say that doctor has killed their patient. And the doctors are even many times beaten up, even murdered. The problem lied only on that, can you ensure that the calibration of this defibrillator be done accurately? And we took this responsibility. And now, across the country, now these defibrillators are calibrated. And there is a mechanism set up from NPL, it goes to the Godrej BISC and many other manufacturers and controllers. And we have ensured this one. So similarly is the case with all the machines, whether it be your digital thermometer, your blood pressure, your sugar level. So it's a Herculean task to be done in this country. Similarly, for clean environment, the measuring instrument for the pollution are not calibrated. So at one location, if there are 5 agencies, they are putting up their sensors, all the 5 will give you 5 different values, and you do not know which is correct. So in 5 years ago, I made a hue and cry at Delhi to the politician leader that the data is not correct and we need to set up the primary standard for that. And interestingly, India did not have any of our facility for calibration of this one. So either we used to go to America for EPS certification, or we used to go UK for our certification for the MCert. And I'm happy that now India has got our own certification scheme known as the NPL ICS, which has been authorized by and approved by the government of India, has been gazette notified. Now we are looking for setting of this facility. This facility setting will take nearly 3 to 4 years time. So design, everything is made, and hopefully within 3 years time, this facility will come, and all the equipment in this country which are manufactured will be certified in India. And therefore the Make in India, the bridge which I was talking about. So environmental and biomedical, it will come up. So these are the details I will not go into. And this lab was stone was laid foundation by Honorable Prime Minister on 4 January. Similarly, international trade. You see, sometimes with the scientists had nothing to do with international trade. We scientists had nothing to do with this. No, that is not correct. Go and read newspapers. Everybody says that made in China items are poor. They sell us the solar model poor, which is poor quality. They sell us the poor quality steel. They sell this and so. Why do they sell us the poor quality steel? Chinese company, when they sell it to the America, do America ever say that your qualities are poor? Never. Because when America imports any of the material from China, they go there and certify it, whether it is of that quality or not. Because they know how to measure them and how to certify them. But since we do not know how to measure and how to certify, we are reliant upon the Chinese to supply us the goods. So when China says that, okay, we are giving you solar modules, which has got the 25 years warranty, we say, okay, yes, fine. Okay, we accept it. But when they come here, they last only 10 to 15 years time. And that's the problem. Similarly, when we export, you go and see literature, how much of our exports are rejected. 13,334 news appeared in Times of India. Made in India items are rejected in US FDA. 270 tons of rice rejected because there is a pesticide in it. Now what happens? When we try to export, our laboratories, they test it. And they say that pesticide and heavy metals are within the prescribed limit. And we send it. Now when they measure it, they say they know it's a very high level. Now then matter goes to the law of code, industrial law of code. And then they check our capabilities, and then we find that we do not know how to measure it. And therefore, this is a national shame that we cannot quantify for the either import or for the export our materials. And that is the reason because we do not have the knowledge measurement. So basically, that's why the National Metal Institute are so important. Because of the SI units, we have a primary standard and primary standard to the measurement equipment. If they are same, it does not matter. So anything measured in NPL India can be equivalent to NPL UK or NIST USA, and therefore in their country, if this pyramid is followed up. So the reference materials are very important. The calibrating equipment may not be all the time important. So each of the countries, they have got their own trademark reference materials. And in India in 2017, we did made our Bharatiya Nirishak Dravya as a trademark. And as on today, we have got 101 reference material coming in the picture. And they are in cement, chemicals, petroleum, metals, food, materials. And it is not that NPL is making all of them. We have done a collaboration with various people. For example, cement. And suppose I'm so happy that the BND was, dedicated to the nation by Honorable Prime Minister and Honorable President of India in the joint parliamentary session on the budget. All Lok Sabha, Rajya Sabha made a category statement that BNDs are important for the national growth. Say, for example, water, and we want to measure the arsenic in water. Now, if I give a water bottle and say that it has arsenic, and I give the 100 laboratories, those who are testing the water, arsenic in water, trust me, you will get 100 results. It will be very difficult for 2 laboratories to give the same value of the arsenic in the same water. And the reason for that is we do not have the reference standard. So for water and many other things, we have looked into this one, and for industry, for iron, for non-ferrous, inorganic, organic, physical, biological, quality of life, everywhere we need a reference material. And this business itself is a 10,000 crore worth business. And all of, as on today, either we are importing them, majority of them, or we are not using at all. And therefore our quality, which I said import export, is hammering. So NPL, along with so many agencies, those who are interested in the reference material, we provide the metallurgical traceability, they start manufacturing them. And I'm happy that, for example, NCB, which makes the reference material cement, the quality of the cement, they started manufacturing it. We are getting the entire country, and so happy to tell you that we are even exporting to the developed nation because our prices are much, much lower. Similarly for food, similarly for pH measurement, water quality, gold. But we have done a dent, but it is not enough. We have to go very far. So for example, these are the photographs of the water and pH solutions which are available, which are even exported. And all this has happened in last 3 years' time. So we are capable, but only thing is that once we know what to do, once we know what to do, I think we are capable of doing it. Similarly, for Hindustan Petroleum is making for the BND for the petroleum products. And therefore, we have directly gone from Bharat 4 to Bharat 6. Because in Bharat 4, the sulfur content is 50 ppm. In Bharat 6, the sulfur content is only 10 ppm. To assure that it is a 10 ppm, we needed the reference material. And the reference materials are manufactured in India, and therefore the quality of petroleum, nobody now can question us. And that is how the petroleum sector has gone so done so well in the past for the quality assurance. Gold, we have prepared the gold standard for the 49 pure, and we are in the process of making the 22, 18, 20 carat gold also for reference material. The cement, I have already told you that they are being exported even the worldwide now. For instrument calibration, that's a very, very important. And that is a nice story which I have seen. There was one company that was making the stent for the heart. And these stent, they need to have a cross section. And the company, which is based on the imported technology, was manufacturing in Dehradun. And what they have done is that they had the SEM image from the NPL UK. And the SEM they have done in the leading institution in the country. And what they have found that everybody has got a different cross section. Everybody has got a different value of the cross section. And when they came to us at NPL, then we said that the problem is that these scanning electron microscope across the country are not calibrated. I said that you give us, we'll give you the images. So when we give the images, he was so happy because those images were exactly same of they got from the UK. And then I explained them how your equipment is calibrated. And once it is calibrated to SI unit, it does not matter that we measure in India or we measure in America or anywhere, it will give you the same value. Unfortunately, this is not known in India, and therefore we have got a large problems in the country. So finally, the cost of those stunts has become very, very cheaper because earlier they have to send to the stunt to the England, they will get tested, come back, time consumption, this and that. Now they are manufacturing for almost the global. So that is how the manufacturing in India will come up. Various launches of the reference materials in the country. You will be surprised to know that we have got more than 4 lakh laboratories across the country in the various areas. And all these poor laboratories, nobody bothers about their quality testing. They are underpaid workers. They get only 10,000 rupees. They have been given an instrument. They put their sample into the instrument and get the test report without knowing whether it is good or not. So the training should be given to that. Reference materials should be given to that. So therefore, the BND has become such a big national project. And I think the university system should also some point of time should come under this kind of contribution to the nation. They should not always remain as an academic institution. So some part of that should go towards the direct contribution to the nation. And the society, you see, many times these multinationals, you know, when we take the wafers packet, they say the 10 gram, but actually it is a 9 gram. Now that 1 gram loss, we never care about it. But if you look from the national perspective point of view, I was shocked that we sell about 1 crore packets per day in this country. Of course, 140 crore people, 1 crore packet is not a big deal. Now 1 crore means 1 crore gram. 1 crore gram means how many kilogram? You multiply that value, how much money we are losing out. And this nobody is caring about. And that is only one product. Look, all the products. So how much money is siphoned out from this country just because we do not know how to measure accurately. And that is the what one should really look into that. And this is the wall which I got painted at NPL to make people aware of that measurements are so critical if you want to make your science scientific. You can publish a paper, but that paper is only a publication. That is not a scientific paper. It does not give you the knowledge. It will not give you that knowledge which is converted into the wealth. Similarly, technology. Why we fail in technology? Because I explained again and again that because our measurements are not correct. Why we could not clean our environment? The biggest Ganga project that we will make it clean. Okay, cleaning the cloth, plastic is one big thing, but cleaning the chemicals in it. When the industrial sewage goes in and then one says that there's a chromium, but we should know how much chromium is there. So cleaning will take place only when we know what is the exact amount of heavy metals lying in the Ganga river. So the cleanness everywhere will take place only first we measure it. And once we measure it, then we know how to clean it up. Healthcare affordable. Most of our patients are due to the wrong diagnosis. If you go to a doctor and he say that you are diagnosed with a medicine, blood pressure, chances are that his blood pressure machine is not calibrated. And once you started taking the blood pressure medicine, you continue taking this. Many times, the diagnosis of disease is given wrong. So, if diagnosis is made correct, half of your problem is done, and therefore the healthcare will become affordable. International trade becomes barrierless. Otherwise, either we import poor quality materials or we export. Our exports are rejected. And the policies, we are not able to make a good policy in this country because it is not based on the calibrated data. And I can give a hour-long discussion on this policy making, how bad policy we make because we do not know the correct value of measurements. But this is not the time for that. So the ASWAL model, which eventually evolved and being appreciated worldwide, that whatever we do in this globe, the measurement traceable to SI unit is the first criteria. And if we achieve that, I think the economy and quality of life will be easier to do that. And if time permits, please do order this book for your library. This is good for everyone, for students, for everyone. It is very, very important. And the final thing which I would say that measurement is the first step that leads to control and eventuality to improvement. If you can't measure something, you can't understand it. If you can't understand it, you can't control it. And if you can't control it, you can't improve it. So that is the gist of today's talk. And I wish the organizer for a good success of this conference. But I definitely would like that please ensure that when you are doing the measurements for any material property, whether they are correct or not. Are we calibrating our equipment regularly or not? And I'm so happy that after 4th January, most of the government, including Maharashtra government now, they have allocated a special fund for the quality assurance, okay, which was not there. So most of the government now, they are funding the startups or maybe even the university system for calibrations. Most of the time we buy equipment, we never calibrate it. We depend upon the manufacturers. Now, the buzz is that until unless we have got the calibrated equipment, we are not going to do any of the things which I said. And I hope I could communicate what I wanted to communicate. Thank you. Thanks a lot.
Thank you very much, sir, for sharing your deep knowledge on the research policies and the measurements. Your talk was full of enthusiasm and valuable knowledge. It will be a great pleasure for all of us to listen you again and again in future. Thank you. Thank you very much, sir. Now let us have the pleasure of listening to our Honorable Vice Chancellor, Madam, Dr. Mrunalini Fadavnis. Please, Madam, over to Madam.
Yeah, namaste to everyone. At this National E-Conference on Materials for Emerging Technology 2021, I welcome you all. Professor D.K. Aswalji and all the distinguished members, keynote speaker, resource persons, all my fellow colleagues, students, and my dear friends. I'm really happy that on a very important topic, School of Physical Sciences and our IQAC cell has organized. And really a pleasure to listen you, Dr. Aswal, that you have given us a true picture that really where we are lacking in terms of measurement. So this is really very important from the point of view, as you have said about Aswal model and inclusive growth, the word which is coined, you can say 10 to 15 years back in the terms of the development of the planning process, or we can say in the 5-year planning, we always talk about this. So inclusive growth has a wide meaning, but you have talked about relationship between the knowledge and wealth. I do agree. And I used to say as just 2.5 years back when I took the charge, I took first initiative how to develop the patents in the university. And sir, I'm happy to tell you that the School of Physical Sciences has a leading role in that. And our all professors and students are really working hard on this. Even on the different areas, we have also gone for the copyrights and other patents for other schools as well. So the promotion of this IPR is very, very important from the point of inclusive growth. But as your Aswal model, which is shows a holistic approach, I should say, and therefore the development of skills, development of quality infrastructure is very close to heart as a person from economics, I should say. Because in econometrics, we have also talked a lot about the measurements, the formula, which is related to the policy formation. And as you have rightly said, it is a first step. And therefore, the quality infrastructure is a need of the day. And therefore, we keep on saying when we are focusing on the modeling part in the econometrics, we always say that there should be quality infrastructure for everything. And therefore, the value addition matters a lot. A small value addition in whatever is the existing thing will definitely change your system, change your GDP, change your line of thinking in investment as well. Because if you are investing in such an area where at present, as you have said, make in India or startups, stand-ups and all these words cannot be like an ornamental thing. We have to think very deep on these issues, that how and when our entrepreneur, our scientist, our social scientist, and all those who are related to these areas can reach to the such type of issues, which is very, very necessary to make India a very vibrant or emerging economy. And therefore, I always agree that this model which you have given has to be supported by various interdisciplinary areas. And the other part which I have also started in the university, like as you have said, that some of the people are very good in physics and some of the people may be very good in chemistry, some of the people may be very good in economics, but they don't have the collagen, they don't have the blended approach, and therefore there we are lacking. So I have also tried for that in the form of giving some multi-dimensional, or I should say the multidisciplinary approaches in the research. Some of the people from different schools, they have completed. Even the School of Physical Sciences is also in that. So that is the thing which we are looking forward. And therefore, this model, which is given by you, is also telling us a truth, which is we are talking in a different way, that a small amount which has been invested in India by the multinational corporations, and suppose we are paying to them, how much money is siphoned out. We are talking the money measurement, how the money has been siphoned out from this particular product, which is really dangerous for us, that we are pouring our hard money for the development of the multinational corporations. I have taken the same words which you have taken for the measurement system, which you have informed us in a very scientific way. So thank you very much for that. But other things which I really wanted to put for our community as a researcher, this emerging material as well as the advanced material, I should say, it is a no exaggeration to say that prosperity of modern and manufacturing economics is dependent upon the innovative development. And when we are talking about the economy and the development, these two are very important words. They are closely related with the R&D, research and development. And therefore, the use of material which satisfy the need of the market, I should say, I can use the word the consumer as well, the client as well, because that is the leading person, what exactly we want, where we have to drive our system. And for that, we should understand the current needs. So current need, market-led operations, as well as the consumer's interest or the consumer satisfaction is very, very important, not only from the point of view of the present system, but the future ones. I think there must be a lot of materials which will come in futures, and that will decide the line of thinking, will decide the line of development, will decide the line of startups in coming years. Even at present, I would like to share all of you that starting or thinking of the startups on the lines which sir has said, or rather we are also preparing, is not an easy task, because starting startups are like they need a different entrepreneurial training, as well as whatever you have, the hardcore training in your own subject. It may be physics, it may be chemistry, it may be anything, but that need a different type of training. And that part is also lacking in our education system, not even the education system, but the ministerial level, which they have started various good things right now, like MSME is doing all these things, but still we don't have a proper, what you can say, the gel or the blend in that. And therefore, that type of thinking related to the advanced material or emerging material, it is interdisciplinary connection. All these has gained a attention. Definitely, the recent past is good. We are thinking on all these things, but still we have to make an unprecedented progress in this area. So we have to think in a very different way. So we merely have to think to change. The electronics industry has brought all of us our lives. I'm talking of the 30 years back, when semiconductors, the silicon-based semiconductors, they were the, I should say, the driving force, the development path, and they have changed a lot. So like this, in coming years, or in the present system, what we supposed to think about the economic background we should have, like we have, or the world has observed 30 years back. Similarly, in next 30 years, as our new education policy also says, that 2030, 2040, 2050, all these steps or the decades they have decided that what type of background we should convert to understand in all the subjects, not only in the physics, but all the subjects. But yes, the hardcore subjects like physics need more attention, more thinking on these lines, that how different things can happen, or innovative and creative things can happen in the country. I always think about the two keywords which is related to especially such core subjects, that is business development and product development process. So these are very closely connected to the 5 features, what I feel. Though I will give some examples, which is very, I think, very familiar to all of you, because you are all from physics, but just to place some examples, I think it is necessary. Like PV, that photovoltaic module, which has been developed, and the feature which I was talking about, the 5 features, which is very, very necessary in the emergence of the novel technology, that is the radical novelty. So this radical change, radical system was there in, for this example I have taken, like in PV. So solar systems we have developed, and converting light photons to electricity voltage. These are the things which has happened at the world level. But when we are thinking of the PV glass, engineering, architect, all are very important, but now the diversion has come to the agriculture. And what we can do for the agriculture in the source of radical novelty, then fast growth. Can we think how this agriculture system can give us a relatively fast growth, and how such technologies, how this emerging material can be useful in such areas. Similarly, another example which is also well known, that is aluminum nitride, ALM. And that is, ALN is the solid nitrate of aluminum, which is highly, we can say, it has been talked that it is used in mobile phones. So that is the research that has all things which has been developed, which is high thermal conductivity. And I think that this type of studies has been done in all the universities. But again, I am focusing your attention towards how the business development has been done and product development process has been done. What is the coherence we have received from all these things which we have already developed, and the new material which will come, how our researchers can think about the prominent impact. As your model, sir, has also said some of the areas which is related to the all these features which I am talking about, the emerging of novel technology. And another part which is related to the RTM, that is resin transfer modeling. One small example, just I have to relate all these things with the features, that's why I have to, that this is the fabrication process, as you know, but other things which is related to molding, and the situation which is related to the reinforcement of fibers like glass, carbon, natural plants. In the natural plants, we can take the fibers like sisal, banana, hemp, flax. All these are the things which is really very, very important from the point of view of the emerging novel technologies. 5 components: radical novelty, relatively fast growth, coherence, prominent impact, uncertainty and ambiguity. These are the emerging features in the technology, where with these 3-4 examples, we can think in coming years what exactly our technology or our economic system will give a direction, or in which way we'll able to go, which we'll able to understand to make India very robust, or to make India very promising country, emerging country. So therefore, these things we have to understand. But one more thing will come, that is environmental impact. And then whatever we are using, whatever the emerging and advanced material we are using, what will be the environmental impact? As many things, as you have also said, which is related to nanotechnology, polymers, as well as when you're talking about the plastics and all that, I think the question comes along with that is the environmental impact. So these are the things which with these talks, which is we have organized today with the help of physical sciences, it's an interdisciplinary field where I say we should understand this first, because we are moving along with all this knowledge in a particular system, understanding only physics, understanding only economics, understanding only one particular area. But when we'll enter in the field of interdisciplinary field of science and building, joining extensive variety of commons and what human really need, what type of structure, combinations, executions, material handling, or whatever is there, is very, very important to understand. And therefore, whatever the name you can have for the material, this emerging material technology will definitely give a sustainable approach in coming years. As you have also rightly said, in Sustainable Development Goals, which has been given by UN, we have also a national policy of Sustainable Development Goals, national policy on SD, we do say. So this is also the year which we are passing through, that is up to 2030. We need to prove about the development of technology. There is one aspect given in the Sustainable Development Goals by UN as well as in our national policy, that how this technology can be useful for the multifaceted management or multifaceted point managing the things. So that is also the thing where we need to understand. And actually for the young students, young researchers, even young teachers, if they keep on doing such type of specialized advancement in the field of physics, the dynamics, which is constantly for the improvement, that will be wonders for our country. And actually there we are looking forward how our students should get a movement towards the startup. It has been also rightly pointed out that we are not only working for getting promotions and getting our salaries and getting some advancement, that is the routine thing, but whatever extra or in absolute manner we can give to our country, that we have to think. And that type of research, that type of patenting, that type of whatever the word you can coin, which is very important from the point of view of the development of our society, development of our consumer, will be really a need for any country, but especially for India when we are talking about the startups and emerging technologies. So this is a small, I should say, effort has been taken by our IQSC cell and School of Physical Science. But the day-long discussion, the day-long experts, what they will going to tell about what is the need of such type of activities, and we need to understand the functionalities in coming years. even the early stage of technology, if the students can able to understand, and we can move towards all composite areas which is related to the subject as well as the need of the economic development. That type of blending is necessary in coming future. So I wish you all the best for the discussions, for outcome. And the outcome is very, very necessary, that whatever you are getting from this webinar, it should come in place of doing something which is very important from the point of view of incubation, development, getting something new in the research, some new ideas, then coining such things which is like a model or like a system, and which will be definitely useful for the university. But at the end, we always say that it all should be useful for the society. So again, I thank you everyone for arranging such a good job, and I wish you all a very good luck. Thank you.
Thank you very much, madam, for your encouraging words and elaborating the ASWAL model for inclusive growth, and also throwing the light on emergent materials and related technologies. Thank you very much, madam. Now I request Professor S.S. Suryavanshi sir to put the vote of thanks. Over to Suryavanshi sir.
Respected Honorable Vice Chancellor, Madam of Punyashlok Ahilyadevi Holkar, Solapur University, Solapur, Dr. Fadnavis, Madam, today's chief guest, Dr. D.K. Aswal, sir, Director, NPL New Delhi, and all my colleagues and student friends and researchers. I'm here to put the vote of thanks of this inaugural function, which is National E-Conference on Materials for Emerging Technologies 2021, organized by School of Physical Sciences. First of all, I would like to extend my sincere thanks to Honorable Vice Chancellor Madam for encouraging us to organize the scientific event via online platform. I sincerely thank Dr. D.K. Aswal sir for sparing his valuable time with us and also motivating the young researchers. I thank the convener of conference and director of School of Physical Sciences, Professor V.B. Patil, for organizing this event. I thank to the university officials for extending their constant encouragement in arranging the e-conference. I thank to young researchers and students for attending the scientific event, and thank to the speakers for accepting our invitation to share their research experience with us. I thank IQSC members and Gardi sir in organizing the conference link. With these words, I wish all of you, especially the young talents, to enjoy the research field. With the kind permission of this president, I declare the inaugural function of the today's conference is over. Thank you very much. Have a nice day.
Thank you very much, sir. Thank you for the vote of thanks. A small announcement over here is we are shortly starting the keynote address. So stay tuned. The session will be handed over to Dr. Banki madam. Thank you. Thanks a lot to everyone.
Good afternoon, one and all. I am Uzma Bangi. I welcome you all to the second session of the National E-Conference on Materials for Emerging Technologies 2021. In this session, we will have the keynote address from a renowned scientist, come academician, come administrator, Honorable Professor P.S. Patil, Pro Vice Chancellor of Shivaji University, Kolhapur. I invite our young, dynamic, and enthusiastic Director of School of Physical Sciences, respected Professor V.B. Patil, sir, to kindly chair this session. Sir will introduce to our keynote speaker. Please, sir, over to you.
Thank you, Dr. Bangi, madam. Namaskar, Professor P.S. Patil, sir. It gives me an immense pleasure to introduce you the keynote speaker of today's conference, Professor P.S. Patil, sir, Pro Vice Chancellor, Shivaji University, Kolhapur. Professor Patil, sir, has taken over the charge of Pro Vice Chancellor, Shivaji University, Kolhapur in December 2020. He has a 31 years of teaching and research experience in the field of renewable energy, that is the development of third generation solar cells, energy storage devices like batteries and supercapacitors, chemoresistive toxic gas sensors, electrochromic, smart window coatings, materials, nanofabrics and nanomaterials. His dedicated work has enlisted him in the world top 2% scientist list published by Stanford, USA in the last month. He has 492 international publications in reputed journals and 5 patents. He has produced 45 PhD students. He is a recipient of prestigious DAD Fellowship, Germany, and Brainpool Fellowship, Seoul National University, and Chonam National University, South Korea. He is a fellow of Institute of Physics, London, UK, member of National Academy of Sciences, India, and fellow of Maharashtra Academy of Sciences. He has received Best Teacher Award of Shivasti Kolhapur in 2014. He is one of the top 10 knowledge producers and outstanding research faculty in India by career 360 ranking. Professor Patil sir has established School of Nanoscience and Technology in Shivasti Kolhapur. He has worked as a member of several administrative bodies of the universities like Senate, Management Council, and Academic Council. He has shouldered the responsibility of Dean Science and Technology, Faculty of Shivasti Kolhapur. His contribution to both academic and administrative work is remarkable. It is our great pleasure that Sir has taken over the time from his busy schedule to give the keynote address for today's National E-Conference on the materials for the imaging technologies. Thank you, sir, for accepting our invitation for this keynote talk. Thank you. Over to Dr. Bangi, madam.
Thank you, sir. Now, I humbly request respected Professor P.S. Patil, sir, to deliver his keynote lecture entitled Nano Textiles, Synthesis, Characterization and Properties. I request you, sir, to share your presentation. Please, sir, over to you.
Okay. Am I audible?
Yes, sir.
Yes, sir.
Okay. First of all, thank you very much for inviting me over here as a resource person at this National E-Conference on Materials for Emerging Technology organized by School of Physics, Solapur University, Solapur. So today I have selected the topic related to nanotextile, which is totally new to all of us, I guess, because we have started working on this nanotextiles for the last 2 years when RUSA has sanctioned the Center for Nanotextile to Shivaji University, Kolhapur. So I will begin my talk because I have another meeting at 12:45, so I have to rush. So let us, I will share my screen. Just a minute. Is it visible?
Yes.
The slides are visible?
Yes.
Yes, sir. Yes. Please continue.
Okay, let me see whether I can start slideshow. Okay. So this is the first slide. So let me go to my antimicrobial nanotextiles. So this is the title of my talk, Antimicrobial Nanotextile Synthesis. So far, we have done a lot of work related to inorganic materials, but this particular challenge was totally new because we know that the textiles are currently attracting a lot of attention because we need some additional functionalities in your textile. So with this particular attention, along with the collaboration with DKT Ichalkaranji Institute, we have started this work in producing nanotextile. So nanotextile, I would like to tell you some historical moments and some of the issues that we have undertaken. And what additional functionalities can be added into the textiles that I will tell you. Our intention was to prepare antimicrobial nanotextiles. So I will narrate the success story of antimicrobial nanotextile. So this is the textile material which can kill the bacteria. Not only that, this is the material which can even kill the viruses. So as far as pandemic COVID-19 is concerned, all of us, we are very much aware of the viral infections and viral diseases. So along these directions, also we are trying a lot. And if our shirts, our textile materials can kill the bacteria and viruses, that will be a wonderful idea. So the mask even can have a certain material, which is a magical material, which can kill the viruses like coronavirus, will be highly beneficial for our health. And in that particular direction, we are working at our School of Nanoscience and Technology. So virus is the extreme condition, extreme case. Before virus, we can also we shall also have to fight with the microbacteria or bacterial infections. The bacterial infections are there. Tremendous amount of bacterial infections can be found in the hospital. That is also called as hospital-acquired infections. So if your shirts or coats or your bed sheets are coated with the antimicrobial nanotextiles, you can avoid such type of infections. And this can be done with simple nanotechnology. You have to impregnate textile material with some nanomaterials, or you have to embed some of the nanoparticles into the textile material, and then that particular textile material will become antimicrobial or antiviral. So let me show you. This is, okay, I will skip this. Okay, first of all, as we know, this is an overview of the work that we have undertaken at Thin Film Materials Laboratory, but I will not go in the details of this. So I will directly come to the online overview of the presentation, outline of the presentation. So first of all, I will talk about some introduction to the nanotextile. What exactly is the need of antimicrobial nanotextiles? What is the international status? How to synthesize, and with the help of deposition techniques, some of the theoretical background related to nanotextile preparation only. We have utilized sonosynthesis techniques. Therefore, I will give you some brief background about sonosynthesis of silver nanoparticles deposited cotton fabric and their antimicrobial activities. And we have also tackled the green route of synthesis of silver nanoparticles. Again, we have also synthesized zinc oxide nanoparticles by using a novel single-step sonosynthesis technique. And we have embedded these zinc oxide nanoparticles into cotton fabric. Zinc oxide can also work as an antimicrobial, and it is non-toxic, and therefore a lot of people can use zinc oxide embedded antimicrobial textile materials. Then we have also done some attempts of incorporating selenium material into the nanotextile, and selenium is very good in killing the bacteria. So selenium has been added into the textile material. And we can also impart superhydrophobicity into the textile material by using padding technique or surface modification technique. So all this story I'm going to tell you. It is a very simple idea, and you can, with a simple modification, you can modify your current technology to the textile technology. Okay, these are some of the materials that we have synthesized in our Thin Film Materials Laboratory. These materials are nanomaterials. They have different size and shapes. And as we know, as the size and shape of the material changes, the properties can also be changed. So you can see here in the first picture, we have shown the very high quality titanium oxide nanotubes. Then you can see in the second ACM photographs, that is titanium oxide nanofibers. Then in the left bottom, you can see nano sheets of tungsten oxide and many other hierarchical nanostructures that we have synthesized in our laboratory. So this is the case that we have got expertise in synthesizing the nanomaterials in different shapes and sizes. And now we have to apply this technology for the textile. Here we have utilized the substrates such as metallic substrate. We can also use a glass substrate, but now we have used the textile substrate, the cloth. Textile is a cloth. So we can use a cloth as a substrate, and on that particular cloth, you can deposit the material. Okay, so this is the nanotextile, the textiles or textile products in which nanotechnology is used during the production or finishing stage. There are different categories of products from the nanotextile. You can have a nano coating, you have the textile material on the top of the textile material, you can coat with the nano coatings. So this is a nano coating. You can also have nanofibers as a wave. Production of carbon nanotubes by electrospinning technique can be utilized for this particular purpose. And you can also have integration of nanostructures into the yarns. So for example, zinc oxides can be integrated into the yarns and you can embed zinc oxide materials. Normally, the technology that is useful and that are used in the industry, some of the industries abroad, not in India. In abroad, they are using the padding technique in which this particular solution is there. And in that solution, some silver nanoparticles or zinc oxide nanoparticles are suspended. And the yarns or fabric is allowed to flow through this particular solution. And they can be, this particular fabric can be extracted. And while extracting, they can squeeze it. So squeezing, that is pressing, will result into the coating of the nano material onto the top of the textile material. This is called the padding technique. But this padding technique, which is widely utilized in most of the industries abroad, it is not that stable. So we have to, because, you know, after one day wearing, we wash our shirts or saris or bed sheets. So washing cycle is very, very important. The coating that we have utilized on the fabric should be stable enough. If that coating goes away or wash off within one cycle, then the next day, that particular textile is no more a nano textile, but it is an ordinary textile. So stability is very, very important. In the padding technique, you can at most reach up to 20 washing cycles. The coating will withstand onto the fabric for the 20 washing cycle at about say 60 degrees Celsius temperature. Because if you put your textile into the washing machine, or the washing machine has a slightly higher temperature. So that particular temperature and then another, extreme conditions should be there. So all this coating should withstand these harsh conditions. Therefore, padding technique currently has washing cycle stability up to 20, and we have to increase it up to 50 or 100. So that was our main aim. So our main aim was to synthesize nanomaterial, incorporate that nanomaterial into the fabric by using some of the techniques which is not similar to padding technique, and then increase the washing cycle stability of that fabric technology. So that was our main aim and main objective. There were a lot of challenges. Then we have utilized the technique which was not there earlier. So that technique is called as sonolysis. The sonolysis technique has been utilized by several people. Actually, the nano materials or nano textile has been brought into the market by Dr. David Sohn. So he's a professor, basically. He did a lot of work into the laboratory. And once everything was successful, he established his own company. That company's name is Nanotex. This is a company who Dr. David tried to use nanotechnology for adding unusual properties to natural and synthetic textiles without changing the fabric's intrinsic properties. Fabric's intrinsic properties are very, very important. So one cannot alter the intrinsic properties of the fabrics after the nanotechnology coating is there. So nano coating can be applied without sacrificing on the intrinsic properties of the fabrics. That was the challenge. But he succeeded in establishing the first nanotechnology-based company, Nanotex, in 1998. And after that, you can see most of the shirts are available in the market, which can be called as a Nanotex. And these nanotext shirts are available in the market. They are super hydrophobic. They are stain-free, anti-stain fabrics. So currently, even in India, in any shop, you can get that particular shirt. So while drinking the tea, if the tea is spilled over onto the shirts, or while eating the food, if the food gets spilled over onto the shirt, the stains will not be there. So it is super hydrophobic textile material, and that super hydrophobicity is imparted because of the incorporation of the nanomaterials like zinc oxide. So this is a very successful story of adding super hydrophobicity to the textile. And after David Sohn, another scientist who is called as Aaron Gedanken, he has also invented and established another company called as a nanotextile. He is from Israel, and he has published very few papers on the nanotextile. And after the successful acceptance of that particular concept by the people, he established an industry in Israel called as a nanotextile. And because of these two initial success stories, people from India, they have started doing work, and IIT Delhi has established a very big center related to the nanotextile area. Not only that, our ARCI Hyderabad is also doing a lot of work related to the nanotextile. But still, it is being carried out at a very few places like IIT and ARCI. Not much of the institutes, they have undertaken this particular project. Since we have advantage of having a textile institute in Ichalkaranji, we joined hands with the Textile Institute. They also have Center of Excellence in non-woven fabric technology. We visited that and we exchanged our ideas. They are expert in textile technology. We are expert in nanotechnology, and therefore we can integrate nanotechnology into the textile technology to come out with something very special, nanotextiles. So that was our idea. And we then had approach to the RUSA, and RUSA has given us a lot of funding for that. Through that funding, we have now established very wonderful facilities in our laboratory. That is the first time we have introduced vessel sonolysis technique, which is not there in India anywhere in the lab. So we have established that particular facility for the first time in India, and we are looking forward to commercialize that technology very, very soon. So in short, you can have a textile and you can add different properties to the textile, and depending on the properties that you need, you can choose or you can select the materials. For example, super hydrophobic textile is the first example. So you can add this functionality, additional functionality to the textile. For that, you can use the material like zinc oxide. Zinc oxide is a very good super hydrophobic material, and you can incorporate that zinc oxide material into the textile so that it imparts a super hydrophobicity. And that's all. So this is very simple. You have to change the substrate material from glass or metal to the textile material. Okay. The only limitation over here is that since it is a textile material, you cannot raise the temperature. The processing temperature should not be 400 or 500 degrees Celsius. It should take place within less than 50 degrees. So if you can facilitate that particular reaction at room temperature, it is more better. But again, the lower temperature or room temperature will decrease the stability of the nano coatings in the textile. So that is a trade-off that you have to obtain between the stability and the processing temperature, the stability and the synthesis temperature. So all these are the very challenging issues that you have to come out, and that can be solved by optimizing properly. Another functionality that you can add into the material is antimicrobial. So you can make your own shirt to kill the bacteria, and accordingly you can embed the silver nanoparticles into the textile material. Not only that, currently you can also have self-repairing textile. So if the textile material or your shirt gets torn off, it will repair on its own. That is called a self-repairing textile. It is a very modern way of textiles. Then you can also have some sensors embedded into textile. If the textile becomes, some part of the textile material becomes conducting, that also we have done. The textile materials basically, as we know, is electrically insulating, but we have converted that electrically insulating fabric into electrically conducting fabric. And if you can do that, you can embed sensor into the textile material, and your shirt itself will act as a sensor, and a lot of advantages are there. Not only that, you can also have fire retardant textiles. So the people or workers or the companies who are doing work related to some high temperature or fire or something like that, flammable things, then they can wear the simple shirt which can retard fire. So you can impart this particular property into the textile by embedding certain nanomaterials. So the textile simply which can catch up the flames very easily will not catch up the flames if you have a nanomaterial to it. So therefore, it is called as a fire retardant textile. Even you can have thermally insulating textile, just like in the very harsh winter season, we use coats and jackets. The jackets are basically very thick and costly and very difficult to maintain. So the simple shirt, a daily wear, we use a daily wear shirt. If that particular shirt becomes insulating to the thermally insulating material, then you can avoid wearing very thick shirts. Basically, this particular technology can be developed for the soldiers who are working at extremely low temperature in Himalaya and near Pakistan, because they have to carry a lot of weight because of their shirts and their textile material that they are wearing. So thermally insulating properties can also be imparted into the textile by embedding several special nanotechnology materials. You can also use UV blocking textile, the textile that can block UV ultraviolet radiations. You can also impart ultra high strength to the textile like a bulletproof jacket. So all these wonderful properties can be imparted into the textile simply by selecting and embedding and incorporating nanomaterials into the textile. So this is super hydrophobic nanotextile. Zinc oxide nanoparticles can be deposited along with HDMS, modified cotton fabric. So you can see here, we have done some experiment and we got successful results in converting our normal routine textile material into super hydrophobic. Then antimicrobial textile can be obtained by incorporating silver nanoparticles into it. And you can see we have studied the antimicrobial activity of silver nanoparticles into cotton. This particular white piece is nothing but our textile material. So this is the textile material. H1 is the sample name. And you can see that zone inhibition technique we have utilized to quantify the amount of bacteria that are killed by this textile material. So silver nanomaterial is a very well-known material which can kill the bacteria very easily. But when we embed that material, silver nanomaterial, into textile, even then it is as effective as it is. So it is very nice. We have done this particular thing very, very successfully. UV protecting textiles can be synthesized just by giving the nano coating of titanium oxide. As we know, titanium oxide is a wide bandgap material and it can absorb ultraviolet radiations and it can be transparent to the UV visible radiations. So whatever the ultraviolet radiations are there in the solar spectrum, they can easily absorb that and annihilate. Absorption and annihilation can be done by TiO2 nanoparticles coating onto the textile. So most of the players, like cricket players, they are out, they are playing the cricket match for entire daylight. So for that particular purpose, the people who are working in the broad daylight, most of the, So about 1 to 2% of ultraviolet radiations are there in the sunlight, and that can be harmful to our skin. Skin cancer may be caused due to the ultraviolet radiations that are there in the terrestrial radiations. So in order to avoid that particular thing, you can coat the textile materials with the TiO2, and the TiO2 will block the ultraviolet radiations and protect our body from UV radiation. This is the flame retardant textile, and you can see the silica aerogels or SiO2 can be incorporated into the textile fabric to become the flame retardant textile. SiO2 can be utilized to retard it from the flames. So this is another thing that we are working, not yet completed, but we are still we have started work on this. So similarly, you can embed several sensors into the textile materials. You can have different plethora of different sensors that can be integrated into the textile material. This is your jacket, and depending on your work schedule, if you are working in the mines, if you are working in some industries, accordingly, you can integrate different sensors into your shirts or jackets so that you can protect yourselves. The sensors can give you alarms. They can make you aware of certain danger if it is there in advance. So all these particular sensor technologies are available, but you can now integrate into the textile material. And therefore, textile-based sensors are also very, very important. Then wearable electronic textiles can also be there. As I told you, that textile materials can be converted into the conducting material. And if it is conducting, you can integrate some electronic circuit into it. And that particular electronic circuit can be designed in such a fashion that you can have some electronic device embedded into the textile material. So here in this particular picture, the people have shown that how to glow a red LED light emitting diode, just to connect the light emitting diode to the circuit which is embedded into your textile material. And the textile material, your shirt can enlight the light emitting diode. So all this flexible electronics is coming into the market. It is stable against variability, washability, and other flexibility. So this is very, very wonderful area. A lot of people are currently working in this area. We have not yet started work in this area. Another thing is that, as I was talking to you about this bulletproof jacket or very ultra high strength fabric. So you know, fabric has a limited strength, but the strength can be enhanced by embedding carbon nanotubes and graphene. So graphene, as we know, is a very, very ultra high strength material, and you can impart that particular mechanical strength to the textile by embedding very carefully the graphene material into the textile material. So this work is also undertaken by us. The self-healing materials, of course, it is there in some research papers, but this particular technology is not yet there commercially available. So in short, these are the materials. Depending on the properties that you want to impart to the fabrics, you can select the material. For example, if you want antimicrobial, antifungal, antiviral, or wound healing type of textile material, then you can go for the metallic nanoparticles, silver, gold, platinum. Even copper is good as an antimicrobial. But you have to then optimize the shape and size of the nanoparticles to be embedded and incorporated into the materials. Otherwise, it will be ineffective. Even antifungal, some of the people, they have fungal infection. They might have some allergies, skin diseases. All this can be avoided simply by wearing a very special shirts. So that is a very wonderful thing. Without taking any medicines, your shirt itself will act as a medical agent and will protect your skin. If your skin is sensitive, it can be useful in the protective manner. Not only that, antimicrobial or photocatalytic, UV blocking, and self-cleaning abilities and properties can be incorporated into the fabric by selecting zinc oxide, titanium oxide, aluminum oxide, and MgO type of nanoparticles. Only thing is that now we are well versed with the synthesis of oxide nanoparticles, but now we should develop the technology so that these nanoparticles can be effectively embedded into the textile material. That is not simple. You can deposit, for example, you can deposit zinc oxide or titanium oxide onto the glass substrate very easily at a high temperature with a technique called as spray pyrolysis. But that spray pyrolysis facilitates deposition of zinc oxide only at high temperature, say 450 or 500 degrees Celsius. But at that particular temperature, textile material burns away. So this is not suitable, and therefore we have to come up with something novel technology where with low temperature you can deposit zinc oxide and titanium oxide, and it should be stable. It should be stable against washing cycle. It should not lose the properties like antimicrobial properties or self-cleaning properties. All these are the challenging things. So because when we deposit some zinc oxide material onto the glass substrate, for example, we are not going to wash the glass substrate often every now and then, every day. But if I deposit zinc oxide on the shirts or bed sheets, after 1 or 2 days, I have to wash my shirt or bed sheet. And therefore, the stability against washing cycle is very important here. So all this matters a lot. You can convert your normal fabric into super hydrophobic fabric just by embedding zinc oxide, titanium oxide, and silicon dioxide, SiO2. You can impart high tensile strength by using carbon nanofibers. You can convert that into electrical conductivity, can be also imparted by embedding carbon nanofibers that we are successfully doing at in our laboratory. You can have this chemical resistance, abrasion resistance, and electric conductivity by embedding carbon black nanoparticles. Then fire retardant properties can be imparted by using zirconium oxide, cheddar-O2, and other allied materials. And finally, antibacterial chemical protection and insecticides can be also, that particular property can be imparted to the textile material by embedding metal organic framework material. So all this is wonderful area. And I think you just can imagine what particular properties that has to be added into the textile. Accordingly, you select the material and you optimize the parameters, embed that material into the textile, and that textile will be transformed into a very wonderful textile. What is the need of the nanotextile? New generation application of a specific nanotextile. Customer demand has been increased recently, and you can also fight against viruses and bacteria. Textiles are good media for the growth of microbes and fungus. And therefore, if you wear your textile or shirts for, say, longer period of time, probably microbes and fungus will grow in the textile that will be harmful to your skin disease. And therefore, there is currently a need of nanotextile. But in India, we are currently importing nanotextile from outside. And therefore, there is a need of indigenous nanotextiles. So this is, hospital-acquired infections. The patient in the next bed is highly infectious. Thank God for these curtains. So this type of curtains are there nowadays abroad in some of the hospitals which are with modern amenities. And these are antibacterial curtains. And you can also have antibacterial curtains in the hospitals so that the infection of another person cannot, the infection from the person will not be spread into the ward. And therefore, that this particular aspect has been is coming up at a greater, that has got a lot of importance currently. So we have also done some simulation work related to how our textile material react with the hospital simulation, this thing. So we have utilized our curtains and bedsheets into the real hospital, D.Y. Patil Medical Hospital, and currently we are testing them, that particular nanotextile, for the whether that nanotextile can kill the real antibacteria and viruses they are there in the hospitals. So this is very important. Then you can see that this particular aspect, nanotextile, has been started after 2000. So it is a new millennium technology, you can see. In 2001, there were only 3 papers, and slowly number of papers published in the literature, they have increased. And now, after the people realize that a real potential of nanotextile, after 2010, there is an exponential growth in the number of publications. So So currently now in this year about 2000 papers are published in the Scopus journals. So you can imagine how antimicrobial textiles, there is a demand in the market. So a lot of people now are demanding antimicrobial textiles. So these are some of the companies and work they are doing. There is one company in India which has been supported by ARCI Hyderabad. ARCI Hyderabad has come up with some technology and they have transferred that technology to N9. They are now fabricated. They are now manufacturing these antimicrobial textile materials in India. So, in short, antimicrobial textile need a very good knowledge of chemistry, material science, textile engineering, and even microbiology. So, it is a multidisciplinary area, and you have to involve a lot of people from different disciplines. In my project, I have a chemistry person, I have a physics person, material scientist, I have textile engineer, and I also have microbiologist, biologist, and biotechnologist. And when all these people, they sit together, they can really do something nicely if they work synchronously. So the same thing we have done. Chemistry person is expert in sonochemistry. Therefore, we have started with sonochemistry. This is the center of nanofabrics that we have established. This is the first of its kind in the state of Maharashtra, this center, in developing a technology and providing facility for producing nanofabrics. And our aim is to develop a cost-effective and durable functional nanofabric. And we are taking help of DKT. Not only that, we have also collaborated with the Powerloom mega clusters in itself currently. And they have assured us that if we produce some handkerchiefs or some socks with nanotechnology, they will sell it into the market. So that's that kind of research and innovation ecosystem that we have developed in our university. So I will not go into the details. I will show you some of the important photographs and micrographs because I have some other meeting at 1 o'clock. So as I was telling you about the stability of the fabrics. Once you embed nanoparticles into the fabric properties should not alter. And how to change, how to study the properties of the fabrics, how to characterize the fabric material is very important. Fortunately, we have all the instruments to characterize the fabric material. Not only to characterize the thin films, but to characterize the fabric and textile material, we have all the instruments so that you can calculate textile strength, elongation percentage, air permeability, tear strength, resistance to abrasion, whiteness index, crystallinity of the fabric, thermal stability, surface wettability, stiffness, and dimensional stability. All these properties are very important in the fabric technology. And fortunately, we have all the technology and therefore we can calculate all the parameters very easily. So in fact, this is a cotton textile substrate and for interaction of the nanomaterial to the textile substrate is very, very important. For that, we are using some surfactants. Those surfactants bind the cellulose, that is a textile material, to the nanoparticles. And this is the very simple sonochemistry synthesis technique. This is a simple probe that you can see in this particular picture. This is a probe sonicator that we have. You can prepare the solution and dip that particular probe into the solution and apply some frequency. So ultrasonic frequency will vibrate that particular probe and that particular energy is prepared and that energy is transferred to the solution. And because of that energy, some chemical reactions take place and synthesis take place. And if you put textiles substrate into the solution, that energy in one step, it will synthesize the material and the same energy is utilized for embedding that material into the textile. So it is a single step, low cost method that we have invented. And I will not go into details. I don't want to go into details. Sonolysis technique is very, very important. As I told you, at a particular ultrasonic frequency, it generates a lot of energy and that energy facilitates creation or preparation of the nanomaterial inside the solution, embedding the material into the fabric. So these two steps can be accomplished in single steps. So it is a single step or one step technology. These are some of the instruments that we have to characterize our textile materials before and after incorporating nanoparticles in the textile material. So you can basically compare the textile material before and after incorporation of nanomaterials. And if the properties do not change, then you can say that without sacrificing on the properties of the textile material, you can embed nanomaterial into it. So because of that, we have adopted, we have used all these techniques. So these techniques, you can calculate stress, strain curve, and so on and so forth. A lot of advanced technologies are there. Not only that, CIE lab color coordinate system we are using to check whether your process of incorporation of nanomaterials into the textile decolor the textile. That can also be checked by CIE lab color coordinate system. So this is some snaps of how silver nanoparticles are prepared from silver nitrate solution with the help of sonalysis, and then we can check the antimicrobial cell. So this is a horn that is a probe sonicator. With the help of that, we synthesize silver nanoparticles. In the SEM picture, you can see some of the particles which are there, silver nanoparticles. And this long fiber is a cotton fiber. In that cotton fiber, silver nanoparticles are embedded. And finally, you can see in the last picture, zone inhibition technique. So this cotton nanofiber is able to kill the bacteria. So this is from synthesis to application we have shown in one slide. Only thing is that if your textile material is white, it can turn slightly brownish. That is the only drawback that we have currently. So this is just a sample code number. We have varied the concentration of silver nanopart and microbial properties of the. Here, what we have seen, rather than amount, the size of the nanoparticle is very important. The smaller is the size of the nanoparticle that has been embedded in the textile, better it is as an antimicrobial textile. So size has to be very, very small. So all this chemistry that I will not go into the details. We, as usual, undertake a characterization technique whether silver has been embedded into the textile or not. So we just take this X-rays, then UV visible spectrum, ATR, FTIR, thermogravimetric analysis, all usual and conventional technologies and characterization techniques that we utilize to characterize the nanomaterial. Then we also use a DLS technique to measure the size of the material, size of the nanoparticle, UV visible, XRD analysis, and then we calculate all the parameters as usual. So this is a SEM image of untreated cotton yarns at different magnification. You can see in slide A, cotton fabric yarns. But if I zoom it, you can see it is very about 500 micrometer, 5 to 10 micrometer diameter of the yarn. So you can embed nanoparticle onto the surface of this yarn to impart the properties. Here you can see some small particles, they are sitting on the surface of the yarns. That particular nanoparticle which are sitting on the surface of the yarn facilitate antimicrobial or antiviral properties. We also undertake textile engineering characterization. What we have seen here is if there is only cotton, if I embed cotton with silver nanoparticles, there is a slight reduction in the strength of the material. Strength of the material is reduced by a negligible amount because we are applying some high energy through sonar. But now we are optimizing and we're trying to retain the same strength in the cotton fabric even after solar basis. You can also check this 104 contact angle. So this is super hydrophobic. Antimicrobial activity has been also calculated and quantified. This is again, we have incorporated silver, and we have seen E. coli and other bacteria for bacteria killing, antibacterial activities. Here you can, this is a well-known video clip because these are the bacteria which are moving, and you can see some small particles of silver nano material. And if they are in contact with the silver nanoparticles, the silver nanoparticle ruptures the membrane of the bacteria and bacteria gets killed. It is not allowed to replicate also. It is why you can inhibit the growth of bacteria. This is one paper that we have published, novel one-step sonosynthesis. There are some other sonochemical technique with silver nanoparticles. I will not go into the details, but this is a green synthesis. We have synthesized by using some xylene resta plant fruit extract for the synthesis of silver nanoparticles. And all these are the properties that I will not go into details. Only thing is that I will show you some important reasons here. This is also successful in killing different bacteria. This is another paper, single-step green process for the preparation of antimicrobial textile by wet chemical and solar. Then zinc oxide, titanium oxide nanoparticles, zinc oxide nanoparticles have also been embedded. For that, we have used zinc acetate and ammonium hydroxide solution. Simply, you have to optimize the concentration and other parameters so that zinc oxide with small nanoparticles of zinc oxide are prepared and gets embedded into the textile material. I will not go into the details. These are a lot of properties that we study. You can see these are the yarns, and the surface of the yarn is totally coated and covered by zinc oxide. This is again textile characterization techniques. Antimicrobial activity, and it has also shown very nice activity. So zinc oxide can also be embedded into the textile for antimicrobial activity. This is another paper on zinc oxide antimicrobial property where I use cotton fabric. We have synthesized selenium groups and embedded into cotton fabric. So selenium is synthesized from almond shell extract. Almond shell extract has been used because it is a green synthesis. You can see very nice morphology of selenium group and effective agent as an antimicrobial. So this is again, we have done it, and we have incorporated this selenium into the fabric material. These are all characterization techniques of the selenium embedded nanotextile. Again, this is another paper in the JCS. Very good paper. You can also read this paper. This is sustainable approach to almond skin mediated synthesis of tunable selenium microstructures for coating cotton fabric to impart specific antibacterial activity. Even we are trying to impart anti-mosquitocidal activity. For the anti-mosquito, we normally use good night mats or good night liquid into the home. But if you have a night suit with anti-mosquitocidal coating, then it will repel the mosquitoes. That we are also undertaken this particular activity. Some of the students are doing work in that area. So again, this is related to super hydrophobicity. Here you can see, this is in fact
I think some introduction from the side of the Professor P.S. Patil, sir. Naduki, sir, can you please check the problem? What is?
Yes, madam, we are looking for it. So Patil sir will call directly to PS Patil sir and see any interruption from their side.
Okay.
We are fine from our end. Just 2 minutes, we will be shortly reconnected.
Yes.
We are not able to see his window as well, right? He's completely logged off.
Yeah, yeah.
I think he has lost his internet connection. That's why he has left out. He will be joining shortly. Let's wait for him.
Yes, sir. Yes.
Nadri sir, wait for 2 minutes. Sir will rejoin again.
Yes, sir. We will wait, sir.
Maybe he has a net problem.
Yes.
Okay,
Yes, sir.
we will wait for 2 minutes. You will rejoin again, please.
Fine, sir. Fine.
Fine,
Thank you, sir. Till sir has joined again. Bangi madam, can you put forward the questions that has been asked? So
Nadri sir,
our...
Nadri sir, just a
Yes,
minute, sir. He will join within 2 minutes. Okay, his internet connection is
Yes,
lost.
sir. Okay.
He will join within 2 minutes. Okay.
Yes, sir.
Just wait for 2 minutes.
Okay, sir.
Sir is joining.
Hello.
Hello, yes, sir, you are audible.
I am connected now. So, Rishi sir?
Please continue, sir. Sir, you are audible.
Actually, unfortunately, my internet was lost.
Yes.
And now I've been reloaded through this mobile.
Yes, sir. Yes, sir. Please continue, sir.
And so I have a meeting immediately. But anyway, I was about to finish my talk. So this was related to the story that we have undertaken at Shivaji University, Kolhapur, under School of Nanoscience and Technology, Center for Nanofabrics. So in short, I have told you what we are doing, and definitely the work is in progress. We have not yet finished that particular work, but at the end, what we want to do is we have to embed all these nanoparticles, optimize the condition, and prepare the nanofabric and nanotextile. Many people are there to commercialize that particular textile. So within a span of 1 year or 2 years, we will be able to commercialize that nanotextile technology. there is some technology that we have already transferred to the industry, and hopefully we are now collaborating with them to come up with nanotextile in a better manner. So I hope that this particular topic has given you some new insight into the working of nanotechnology, because I always wanted to develop some technology useful for the society. If I look at the development of the solar cell, there is a bottleneck into the efficiency of the solar cell. As we know, silicon solar cell technology is well established. It has got higher efficiency and higher stability. So if at all you have to develop a competent technology related to the solar cell, your solar cell must be more efficient than silicon, that is more than 20% efficiency and more than 20 years of stability. And that particular ecosystem is not available in India, and therefore you can do only research. Our inclination was development or translation of research into technology, and in that way we have undertaken this nanotextile area, and within 1 or 2 years we have done substantial progress in the synthesis, characterization and studies related to the nanotextiles. So I would like to stop here, and if there are some quick questions, I will be here to answer these questions. Thank you so much.
Thank you, sir, for such an informative and fruitful lecture. Now the session is open for the discussion. I think there are some questions from the audience. I will read one question, sir.
Sure.
Can we think of these materials for food packaging industries where organic matter will remain for longer life?
In fact, currently food packaging is done in the plastic bags or some tin bags or tin material. We can say that packaged food is available in the tins or tetra packs. So this technology is already there. But if there are many experiments that we have done, and some people have also done for the food technology. For example, if you keep bananas in your house, in the kitchen, for say 2-3 days, the skin of the banana gets blackened up after say 2-3 days. And if you keep the same thing with silver nanoparticle coated plastic, then it can withstand for about 7 days. For 7 to 10 days, the skin of the banana remains as it is after 10 days. The blackening of the skin of the banana is because of the bacterial infection or bacterial invasion onto the skin of the banana, or fungal infection or fungal invasion on the skin of the banana. So bacterial and fungal invasion onto the food skin or food coverage can be avoided with the silver nanoparticle embedded plastic, because there are people who have prepared the plastic bags, carry bags, and bags used for the packaging of the food material with the help of silver nanoparticles. They are already there and they are under use. So many people are now using. I have seen some vegetable market, they are using these type of carry bags, not carry bags, in fact, the bags for the packaging of the food. So when you keep your vegetable in that particular plastic bags, then they are more fresh. So in short, you can avoid fungal growth or bacterial growth onto the skin, onto the upper surface of the vegetable. Thereby, you can make this vegetable more fresh. So this is a very wonderful area, and therefore, but there it is not related to the nanotextile. It is related to the plastic. So you can have some small, some thin layer of nano coating of silver nanoparticles on the surface of the plastic, and you can use that as an antifungal or antimicrobial material to protect your food. So that is also very interesting idea. That's right.
Thank you, sir. Sir, I have one question. As you told, the self-repairable materials. And as you know, silica aerogel is a material which is used for the thermal insulation. So if we dope or composite the silica aerogel with other material, then can it be used for the can it be used as a self-repairable material?
Madam, self-repairable material is difficult because I know that there are several polymers they are used as a self-repairable materials. And I'm not really sure about how and which polymers are useful in self-repair fabric. And the work related to self-repairable fabric is not that great. Therefore, we don't have much of knowledge related to that. I have just told one slide because it is there. It is there, and a lot of work is needed, in fact, in that particular direction. But some polymers, especially, we are collaborating with National Chemical Laboratory Pune. Dr. Vadgaonkar is there. He's expert in that. He suggested me to work in this self-repairable fabric. So let us see. I don't know really exactly which material is useful and applicable to the self-repair.
Okay, sir. Thank you, sir.
Currently, we have concentrated only on antimicrobial, super hydrophobic, simple applications.
Okay. Thank you, sir. Sir, I am happy to share with you that our school, that is Professor V.B. Patil sir and his team, in collaboration with other school or department of the university, have produced the antiviral mask in this pandemic of COVID-19, sir. And currently, our school is not only engaged in the synthesis of materials for sensing and energy storage and conversion, but also on the medical applications.
Good. COVID-19 pandemic has given us that particular vision.
Yes, sir. Right, sir.
Good.
Thank you, sir. Now, on behalf of School of Physical Sciences, Punya Shlok Ahilya Devi Holkar, Solapur University, I heartily thank you for sharing the sea of innovative ideas with us. Definitely, your talk will be helpful or much useful for us in shaping our research career, sir. Thanks a lot, sir.
Thank you very much.
Thank you, sir. Thank you very much, sir.
Thank you, Professor V.B.
Thank you.
Patil.
Thank you, sir.
Thank you all.
Thank you.
I'm also thankful to Professor V.B. Patil, sir, for well chairing this session. Thank you, sir.
Thank you. Thank you, madam.
Thank you. Now I will.
Yes,
thank you, sir.
Thank you, sir. Now it's time for the oral presentation. Many participants have shown interest to present their research work all over India. So here, apart from amongst those, we have selected 5 research papers for the oral presentations. The time for the oral presentation is 10 minutes. And I request all the presenters to complete their presentation within the time. The first oral presentation, OP1, is of Dr. Ramesh Datir. Dr. Datir belongs to the Center for Nano and Material Sciences, Jain University, Bangalore. I request him to share his PPT and start his presentation. Dr. Datir.
Yes, ma'am.
Sir, can you start? Can you share your PPT and start the presentation?
Yeah. Sure, ma'am. So,
the title of his presentation is Greener Pathways of Developing Nanocrystals and Their Applications.
So, are you able to see the screen now, ma'am?
Yes, sir. Yes, sir.
Yeah. So, as you said, the time is 10 minutes, right? So, should I start now?
Yes, sir. You can, sir.
Yeah,
you start
sure.
now.
Yeah. So, good afternoon, everyone. And First of all, I would like to thank the organizing committee for giving me the chance for presenting my work. Although it's a bit short time for me to present the work, but as per suggestion, I just pick up the few things which we are doing currently from last couple of years. Uh, the title of the work, as ma'am mentioned, that greener pathway for developing nano catalyst and their application. The catalyst synthesis we are focused by greener pathway, and for that there are two types of catalysts in general people used to develop for the synthesis of organic molecules or any material application or any semiconductor application. Generally my purpose is to synthesize the catalyst for the organic synthesis application or the drug discovery application, because I basically belongs to the organic chemist. So when I was in abroad country, my most of the work is in homogeneous catalysis. But being a researcher or the active researcher in the diverse field, I don't want to continue the research in the same stream. So I switched my research to the heterogeneous catalysis. Of course, the homogeneous catalysis gives the many ideas for the researcher or the drug discovery people to discover the drug. But of course, at the same time, the heterogeneous catalysis also plays the very important role. So what basically I observe in the homogeneous catalysis, so in the homogeneous catalysis, the insufficient surface catalytic surface area is there. Difficulty in recovery and reuse, because we cannot reuse the catalyst in homogeneous catalysis because it is soluble in solvent. And the deactivation of catalyst towards the end of the reaction, because it will coordinate with the many molecules or the many metal center, and ultimately deactivate. But what observed in the homogeneous catalysis is that the simple product purification, easy recovery, we can reuse, and less leaching of the active catalysis. So the heterogeneous catalysis has the important role. And moreover, it is can be prepared by biogenic ways. So what is the advantage of biogenic synthesis of catalyst? Is easily available, eco-friendly, high stability, biocompatible, rapid synthesis, clinically applicable, green, one pot, simple, and cost effective. So these are the application of the heterogeneous catalysis, or especially the biogenic synthesis of any heterogeneous catalyst. And there are synthesis pathways which we can appear from the like a plant extract, then metallic ion source, and then nanoparticle, and then finally we can synthesize the bioreducing agent, and then growth and the stabilized capped nanoparticle. So the nanoparticle will be available in the form of the kind of leached compound, or the phytochemicals are attached in the catalytic surface. So what is the phytochemicals? So these are like various organic compound in which the OH or the acid or amine, these are many functional group which bind to the catalyst, and ultimately it gives the support to the catalyst, and in that way the role of ligand or the use of a ligand can be avoided. So this is the literature of the heterogeneous catalysis. And how we can synthesize the nanocatalyst? The green synthesis of metal nanoparticle can be obtained from the starch, leaves, roots, flowers, fruits, or honey, or many other materials. So these can be used for the synthesis of nanocatalyst by simply by simply drying and then converting into the extract, and then that extract can be treated with the metal source, and finally we get the nanoparticle. So what is the next point? Once we prepare the nanocatalyst, there are various applications of the nanocatalyst for the hydrogenation, oxidation, CC coupling, C heteroatom coupling, and other material related application. And these are all the emerging technologies for recent days with respect to the heterogeneous catalysis. So what exactly? Because I just pick up the few things which metal nanoparticle are used for the many people for the synthetic application. So for example, here if you can see in the center of the slide that MNPs. So M may be the palladium, M may be the nickel, copper, or any other transition d-block element. And what people used to do, they take these kind of green sources like cinnamon or soybean leaf, some other watermelon or corn or star apple, pepper seeds or aloe vera. So these are already literature people used to use for the synthesis of metal nanoparticle. So on this, because when I shift in this area of research, I am bit new and there is a much challenge to discover the catalyst by our homemade method. So I studied the literature, and what I found that there are many things in the literature or in the nature that can be used for the synthesis of like a metal nanoparticle, and that exactly the Indian research needed in nowadays, because we cannot have much funding for using the costly chemicals, or these are the for example, if you see the papaya peels, people used to eat the papaya and the rest of the material they just throw. So what happened, that material will cause the pollution, the decomposition is difficult. So instead what we can do, we can use that papaya peel and dry under sunlight and use for the further procedure to lead to the synthesis of catalyst. So keeping these things in the mind, we just move to the synthesis of palladium nanoparticle. So how people used to use this green material for synthesis of palladium nanoparticle? For example, this is some literature. People use the black pepper plant. They take seeds and then crush it and then stir with the ethanol and treat with the palladium acetate. Finally, get to the palladium nanoparticle as a black color powder. So what that black color powder used to do, they can be used for the CC bond forming reaction like a HIAMA or the cyanation reaction. So in this way, synthesis of nanocatalyst people use from the papaya peel. And then with this literature knowledge, what I used to do, I take the pepper plant and then cultivation, grinding, extraction and reduction. When we use the to treat that catalyst with the aryl halide, and then aryl halide palladium species will form, and at the same time aryl amine will coordinate with this, and then finally with the removal of nitrogen we will get a CC bond coupling product, and this we published in Tetrahedron in 2019. In the similar way, what I used to do, because people used to do the CH activation reaction and there is a much challenge of reduced selectivity, but what I do that in our group we use palladium nanoparticle or NSC palladium nanoparticle for C2 selective arylation, and more importantly the palladium as a cheap source, reduced selective, it is directing group free, external ligand free, and high turnover and turnover number we obtained, and also there is a no side product and we get the catalyst recyclability. And in the similar way, this mechanism is showing that how the palladium is converted to the palladium 2 is converted to palladium 0. So these phytochemicals are treated with this palladium 2, and then ultimately reduce the palladium to the palladium 0, and also it bind to the palladium 0 and acting as a ligand. And if we take the analysis of that powder by FTIR, XRD, FESM, we can get the clear-cut idea of the reduction of palladium 2 to palladium 0 by the plant extract. And that catalyst we also use for the like a diketo product formation, like enamide oxidation. So if you can see, the people use ruthenium, gold, copper along with very costly ligand and solvent, but we can do with the homemade catalyst to get the diketo compound, which is synthetically important, and at the end we also can recover the catalyst. And these are the mechanism, and also this is the catalyst recyclability study. So for example, in the first cycle we get the 98% yield, but in the even after 10 cycle we are still get the 60% yield, and this is the beauty of this catalyst. So the agenda is only to discover the catalyst and apply it for the organic synthesis application. So and at the second half we also working on the transition metal free chemistry, because a few of the students are working on this and few of the students are working on the green chemistry. And in the recent past we also developed the transition metal functional hydration of alkynes, one pot synthesis of fluorinated beta keto imide using selectofluor. So what we did, that we take the simple aldehyde and amine and treat it with the methanol, and we get this intermediate which is further treated with the selectofluor to get the 1,2-amino ketoimine product, and this we published in the OBC 2019. And these are the various substrate which can be treated or with this metal free condition, and then we get the very selective fluorinated compound, because fluorine has the very much importance in
Sorry,
the
sir, to interrupt you, sir. Your time is finished, sir. Please wind up, sir, immediately.
Yeah. So it's an intimation or to stop the presentation?
Means it's intonation. You have 1 or 2 minutes.
Yeah. That's what. Okay. So then this is the mechanism, and then further we also did that at the same time the cyclodation reaction, which is again the metal free condition, and we also prove that compound by the crystal analysis. And this is the DFT which we done in the collaboration of the foreign university, and also another project which are running on the similar interface to get this larger member 6, 7, 8 member heterocycle, in which we the mechanism is again similar to the OBC paper, and this is already submitted for the publication. So we would like to acknowledge our director and also my team member, and also DST Government of India for the fellowship and financial support. So thank you for your attention, and thanks for the organizing committee and my colleague Dr. Nadargi for inviting me and giving me the chance. So in future I will like to get more time to present this kind of work, because it is very short and I cannot convey the message towards the audience what exactly I want to say. So anyway, thank you ma'am. Yeah, if any question then you can ask.
Thank you, sir, for a wonderful presentation, and I excuse for the for your lack of time, because it is the time scarcity and we have to finish your presentation, and excuse for that one. And surely in future we will give much more time for your presentation, as your synthesis, green synthesis, and it is recently it is much useful, because the chemicals are hazardous and they are much expensive. So we can use the green synthesis for the application in the current era. So I have one question, sir. For the heterogeneous catalysis, is it required the material should be crystalline or amorphous if you want to study the heterogeneous catalysis?
No, it is not necessarily, but most of the cases the material should be solid, because we would like to go for the recovery of the material. So in heterogeneous catalysis, generally the catalyst will not be soluble into the reaction mixture. So in that case, I think the material, it is necessarily to be a solid stage.
Okay.
Yeah.
Thank you, sir. Thank you, sir, for your presentation, and thank you for being with us. Now, the next oral presentation is by Dr. Praveen Kumari Trivedi. She is from Department of Physics, IIT Delhi. I request Dr. Trivedi to share his presentation and share his PPT and start the presentation. Please, ma'am.
Yes.
The title of her presentation is Experimental Investigation of the Effect of Heteroatom Doped Carbon Microsphere Supports on the Stability and Storage Capacity of Nano Cobalt Oxide Conversion Anodes for Application in Lithium-ion Batteries. Please, ma'am.
Yes. Is it visible?
Wait, it's sharing, ma'am. Wait a minute. It has started sharing the screen. Yeah, now it is visible, ma'am. You can start now, ma'am. Please, ma'am.
Okay. Yeah. Good afternoon, everyone. Myself, Dr. Praveen Trivedi. So first of all, I would like to thank for giving me this opportunity to to present my work here. So title of my presentation is Experimental Investigation of the Heteroatom Doped Carbon Microsphere and Nano CO3O4 Conversion Anode for Application in Lithium-ion Battery. So this work I have done in CSIR NCL Pune under the supervision of Dr. Manjusha V. Shelge. So as we all know that we need energy in our day-to-day daily life. So from where this energy comes? So it comes from fossil fuels like coal, gas, oil. But drawback with these fossil fuels is these are limited and also affect our environment and health. So we need clean energy sources like renewable energy resources like hydro, biomass, wind and solar. But the problem with these renewable sources are these are intermittent in nature. Means wind can give energy when we don't need also, and solar can give energy only in day life. So we need efficient energy storage system like capacitors, supercapacitors and batteries. So this is the Ragon plot where we can see that battery is having high energy density as well as moderate power density. So what is battery? Battery is electrochemical energy storage device which can convert chemical energy into electrical energy. And there are two types of battery: primary non-rechargeable battery and secondary rechargeable battery. So these are secondary batteries, among where we can see that among all secondary batteries, lithium-ion battery is having higher volumetric energy density as well as high specific energy density. So how does this lithium-ion battery works? So this is the working principle where we can see that batteries consist of anode, cathode and separated by separator. So in electrolyte medium, so where we can see that during charge, lithium-ion travels from cathode to anode, and during discharge, lithium-ion travels from anode to cathode. And from the outer circuit, electron travels from anode to cathode and generate electricity. So for the better battery performance, this electrochemical potential of electrode, anode and cathode play important role. So this is the energy level diagram of the battery component, where we can see that this anodic potential should be always lower than LUMO of electrolyte, and cathodic potential should be higher than HOMO of electrolyte. Otherwise, electrolyte will get decomposed and battery will get short. So most commonly used anodes are graphite, carbon, tin. Cathodes are lithiated transition metal oxides, and electrolytes are LiPF6, LiBF4, and lithium perchlorate salt in organic solvents like EC/DEC. So my work is in anode material. So there are three types of reaction mechanism occurs in anode: intercalation reaction, alloy reaction, conversion reaction. So during intercalation, lithium and intercalate and deintercalate in carbon type of material. Here theoretical capacity is less, 400 milliampere per gram, but cycle life is very high due to very low volume expansion during cycling. Second one is alloy reaction, where alloying de-alloying takes place with lithium in silicon germanium type of material, where here theoretical capacity is very high, up to 4500 milliampere per gram, but due to large volume expansion, the cycle life of this material is very less. So third one is conversion reaction, where Faradic reaction takes place during charge discharge. This occurs in metal oxide, transition metal oxide. Here capacity, theoretical capacity is 1000 milliampere per gram, but due to moderate volume expansion, cycle life is only moderate. So I have chosen this transition metal oxide, cobalt oxide, because it is having high theoretical capacity, and as well as I have chosen this nitrogen sulfur doped carbon sphere, which gives the stability as well as improve the battery performance. So first of all, with the help of L-cysteine and saccharose, we have synthesized this nitrogen sulfur doped carbon sphere via hydrothermal synthesis. And then again, with the help of, by using this NSCS and cobalt nitrate precursor, we have synthesized this nitrogen sulfur doped carbon sphere CO3O4 nanocomposite. So after synthesis, to further phase purity and crystallographic structure identification, we have done this XRD analysis, where we can see that this CO3O4 this XRD spectrum of CO3O4 conforms the spinal structure of CO3O4 with FCC lattice structure. Here, in this XRD spectrum of CS and NSCS conforms the graphitic nature of the material. So further, to quantify the carbon and cobalt oxide in the composite, we have done this TGA analysis, where we can see that this percentage of carbon and cobalt oxide in the nano composite is carbon is 40% and CO3O4 is 60%. Further, to find out the oxidation state of the metal and the elemental composition, we have done this XPS analysis. So this is XPS survey spectra, which confirms the presence of all the elements like cobalt, carbon, nitrogen, sulfur, and the oxygen. And this is the deconvoluted spectra of the cobalt 2p in NaCS CO3O4, where we can see that this peak corresponds to the cobalt 3 plus, this peak corresponds to the cobalt 2 plus, and this peak at higher banding energy corresponds to the interaction of cobalt species with hydroxyl species. So further, for the morphological study, we have done this SEM analysis. So this is the SEM image of NSCS, where we can see that spherical-like morphology obtained. This is the SEM image of CSCO3O4, where we can see that the aggregated CO3O4 nanoparticle structures present on the surface of the CO3 carbon sphere. And this is the SEM image of NSCS CO3O4, where we can see that extended sheet-like morphology form onto this extended sheet-like morphology of consists of CO3O4 nanoparticles form on which covers the surface of nitrogen sulfur doped carbon sphere. So this homogeneous covering is obtained due to the presence of these heteroatom nitrogen and sulfur, which control the nucleation and growth of the CO3O4 nanoparticles. So these are the elemental mapping images, which confirms the all the elements uniformly present onto the sample. So these are the TM images, where this is the TM image of NSCS. These B and C are the TM images of CO3O4 nanoparticles, where we can see that the average size of CO3O4 nanoparticles is 10 to 20 nanometer, and this spacing corresponds to 220 and 311 plane of the CO3O4 nanoparticles. These are the low and high magnify image of NSCS CO3O4, where we can see that this CO3O4 nanoparticles present onto the cover the surface of this nitrogen sulfur doped carbon sphere. This is the SID pattern, which shows resemblance with the XRD pattern of this composite. So here this presence of this diffuse concentric ring with bright spot confirms the polycrystalline nature of the material. So further moving toward electrochemical characterization, first we have done CV. So this is the cyclic voltammetric curve of CO3O4 nanoparticles, where we can see that this intense reduction peak appears due to the formation of SAI layer and the reduction of cobalt oxide to metallic cobalt. And this is the anodic peak, which is due to the oxidation of metallic cobalt to cobalt 2 plus and 3 plus oxidation state. So these are the CV curve of CSCO3O4 and SCO3O4, which is showing similar CV curve like CO3O4. Here we can see that this overlapping of this cycle, this CV profile after second cycle confirms the stability of the electrode material. Here after second cycle, this intense peak is split into two distinguished peak, which confirms the multi-step reaction occurs during lithiation deletion. This is a charge discharge profile of all three. Here this is here we can see that this NSS CO3O4 gives a high specific capacity around 1057 milliampere per gram. So this high specific capacity as well as high stability is due to the presence of heteroatom nitrogen sulfur doped carbon sphere, which improve the conductivity of the material, also stabilize the electrode by where carbon act as a buffering agent. In case of this CSCO3O4, capacity is reduced because of the contribution of the carbon, and we know that theoretical capacity of the graphitic carbon is only 373 milliampere per gram. So further we characterize these all three material by impedance spectra. So
Sorry, this, please finish within 1 minute.
Yeah, just 2 minutes. So here we can see that this NaClO3O4 gives very less charge transfer resistance as well as very less diffusion resistance due to the improved conductivity as well as improved kinetics of the lithiation and delithiation during charge discharge. So this is the cyclic stability at 1 ampere per gram of current density after 350 cycle, where we can see that this increasing, decreasing, increasing trend appears. So this increasing for the initial cycle is due to the activation of cobalt oxide nanoparticles. Then again, it is decreasing due to volume expansion occur during continuous cycling, which rupture the electrode material. And after certain cycle, again, polymeric gel-like film formation occur, which stabilize the electrode material and gives the stable performance. This is the rate capability of which have done after 250 cycle at 1 ampere per gram of current density. So here we can see that when we are going from 0.1 ampere per gram to 5 ampere per gram of current density, this NaClO3O4 gives higher capacity, higher specific capacity, as well as high stability. Even at 5 ampere per gram, it gives around 800 milliampere per gram of capacity. And when reverting back to high to low current density, again it recovering its high specific capacity. So further, after that, we have calculate the lithium and diffusion coefficient. So here we can, with these two equations, from where we have find out this NaClO3O4 gives very high, gives more diffusion coefficient compared to CO3O4 and CsCO3O4. So after cycling, also we have done post-cycling studies. So this is the TM analysis of NaClO3O4 after 350 cycles. So here we can see that this electrode material retain its structure, and this is the SAED pattern. Here after 350 cycle also it maintain its partial polycrystalline nature of the material. So this is the impedance spectra during cycling. So as I have told, this increasing, decreasing, and then again increasing profile. So here we can see that after 10 cycle, this RCT value is decreased. CTC value is decreased, and again after 30 to 60 cycle, this charge transfer resistance is increasing. And after formation of polymeric gel-like film formation, then again this after 250 cycle, this RCT value is decreased. So which validate the stability behavior of the NaClO3O4 material. So in conclusion, we have synthesized this NaClO3O4 nanocomposite, which gives 745 milliampere per gram of specific capacity at 5 ampere per gram of high current density. And also after 350 cycle, it gives 1285 milliampere per gram of specific capacity at 1 ampere per gram of current density, which is very high. And also it has very less charge transfer resistance in compared to non-doped electrode material because of the heteroatom doping, which improve the conductivity as well as buffer, as well as improve the kinetics, lithium and transport. And also carbon will provide the stability to the electrode material. So thank you.
Thank you, ma'am, for sharing your innovative research with us. One question from the audience is, what is the stability of the nano cobalt oxide conversion anode? How much is the stability?
As here we can see that we have done this stability for the 3 cycle for 3 materials. So this CO3O4 is showing very less capacity after certain cycle only. So we have improved the performance of CO3O4 by incorporating heteroatom with carbon as well.
Thank you, ma'am. Thank you for sharing your research work.
Thank you.
The next oral presentation 3 is by Dr. Manik Rokde. Dr. Rokde is affiliated to the MET Hyderabad. Dr. Rokde, sir?
Yes, madam. Am I audible?
Yeah, you are audible, sir. I request you to share your PPT and start the presentation.
Is the presentation visible, ma'am?
No, yet not, sir. The title of his presentation is Futuristic Semiconductor, Crystal Growth and Challenges. Yeah, no, it is visible, sir. You can start now, sir. Please complete the presentation
Okay.
within the time, sir.
Good afternoon to everybody. First, I would like to thank organizers for convening this conference and giving platform for discussions to researchers. And special thanks to Dr. Nadargi for giving me this opportunity to present one of the CMET Hyderabad's research activity. Title of the project is Futuristic Semiconductor. I will be discussing here one of the futuristic semiconductor, that is silicon carbide, which is a wide bandgap semiconductor which is very much useful for high voltage, high temperature, and high frequency applications. Its crystal growth and challenges. So basically, a quick glance to CMET. We operate at Hyderabad, Pune, and Thrissur. Of course, headquarter being at Hyderabad, which is Pune, and which is taking care of thick film materials. And at Hyderabad, we work on compound semiconductors, ROHs, etc. So it is a quick overview of technology trends in semiconductor. As you know, silicon is a material of choice since last 50 years on so. Due to its low cost, reliability, and established device technology and infrastructure, but unfortunately, India missed the bus on silicon technology because of various technical reasons. But due to that, India is far behind in silicon manufacturing, like solar cell design, etc. Obviously, there are certain limitations of silicon, like operations at low temperature and voltage, low voltage, etc. Even heat dissipation is more. And to overcome that, wide bandgap semiconductors hold promising for revolutionary improvements in size, shape, and cost, weight, etc. So there are few wide bandgap semiconductors like silicon carbide, GaN, and aluminum nitride have emerged as candidate substrate material that has overcome the performance limitations of silicon and other semiconductors. So why silicon? So silicon bandgap is, if you compare with silicon, is almost 3 times, and other electrical parameters, if you compare, they are very high as compared to silicon. So some of the parameters like high background voltage helps in low on resistance, high thermal conductivity, gives opportunity for high power and temperature devices, wide bandgap for high temperature devices and optoelectronics. So using silicon carbide, you can make smaller, cheaper, and better quality and devices. So that's why silicon carbide is very much useful. By using those, we can have high voltage devices, high frequency, high temperature devices, which can carry high current. And of course, you can make smaller devices as compared to silicon. You can make 10 times smaller devices using silicon carbide. And due to its high thermal conductivity, less cooling is required. So these are some of the areas where silicon carbide can be or is going to be useful, like space applications, then your communications area, then high power devices, and high power harsh environment devices for harsh environment. So these are some of the international players, which of course from starting materials, that is starting from growth materials, growth of silicon carbide to SiC devices, they are very far ahead, and India is lagging in that. Cree is dominating that area. So taking into consideration of the benefits of silicon carbide, CMET initiated in collaboration with DRDO, that is growing 6H, as well as we grow 4H SiC also. So catering to the defense requirement. This total activity is sponsored by DRDO with the cost of more than 20 crores, wherein we grow 6H and 4H silicon carbide single crystals having 2-inch diameter. And this is first time in country we have grown this. And we have established advanced SiC single crystal facility at CMET Hyderabad. And we are continuously growing silicon carbides, bowls, crystals, and giving wafers to the DRDO for their defense applications. Our next target is to have semi-insulating silicon carbide, which can be useful for, as an substrate for device fabrics like HEMT and MMS. So this is a quick technology glance for this one, silicon technology. This is our, we use 4H or 6H depending on desired crystal seed. Then you use the reactor, and then you grow SiC single crystal bowls. And of course, silicon carbide is the hardest material after diamond. So required grinding, cutting, lapping, polishing facility itself is a huge task. After that, characterization, you can grow epitaxy on that, and then device fabrication can be done. So what are the challenges before implementation of the growth, and what are the solutions for that? So SiC does not melt at any known temperature, and it can be converted from solid phase to vapor phase. That is the sublimation. And there are two factors like silicon and carbon. They have their vapor pressure differences, and stoichiometric melt is possible only about 3000 degrees Celsius, and which require 10 gigapascal, more than 10 gigapascal pressure. So achieving this itself in laboratory is very difficult. And another factor of getting high pure graphite and polytype stability, whether you want 4H, that is hexagonal, and 6H hexagonal, or 3C. So of course 4H, 6H will grow both more than 2000 degrees Celsius. So if you see this phase diagram, so silicon and carbon made up of SiC is made up of silicon and carbide, comprising 50-50% of atomic participation. So if you see this phase diagram, you have to catch this area to achieve your single crystal SiC. Of course, you have to work on stability of the polytype, single polytype. So this is the frequency occurrence figure, so wherein you can have 4H, 15R, 6H. So why this is polytype stability is very difficult. If you have temperature distribution throughout your chamber, and you slightly deviate from that, so you will get polytype, other polytype inclusions like 15R, 8H, 4H, 2C, 3C, etc. into your desired crystal. So what are the challenges? Maintaining the silicon and carbon ratio is itself is a very big task, and you can optimize that by growth schedule, modifying growth schedule. There are several polytypes. So the stacking sequence of SiC, silicon carbide, and silicon and carbon bilayer in the 001 direction must be non-volatile. Then only you can have your single polytype throughout the growth direction. So there are more than 200 polytypes known. So achieving stable polytype out of that is very big task. Then you need to have purify your graphite and source materials. For that purification and sintering process we followed. Then seed crystal attachment itself is a very big challenging task, having the different polarity and crystallinity, which causes the defects in your growth. So seed crystal attachment and micropap density and other defects. So sometimes crystal growth itself inherent some of the defects like basal plane defects, you cannot negate those, but you can minimize those after optimizing the growth schedule and growth parameters. This is our PVT reactor, that is a physical vapor transport reactor at MET by Axtron, Germany. So this is a reactor section of electrical section. RF heating is required for that, and this is the reactor chamber. From here you can upload and download the crucible assembly, that is the growth assembly. So these are some of the graphite crucibles and assembly we use. This is the seed holder on which silicon carbide single crystal seed, that is the wafer, we need to attach desired crystal growth. Then this is the lower crucible in which we put polycrystalline silicon carbide powder, and this is the heater and insulations we keep in and load. So what is the process? Basically you keep, as I shown here, this is the lower crucible in which silicon carbide powder, polycrystalline powder, source powder is kept, and you attach the seed on this, and you kept here, and you have to heat the RF by RF, using RF, and it is heated in such a way that negative temperature gradient is created, and source powder will be at 2300 degrees Celsius, and your seed will be only less, you say 100 to 150 degrees Celsius less. So the controlling temperature negative gradient is also a very big challenge, and this is we do simulations also. This is the streamlined simulation species transport from within the SiC course to the source. And this is our chamber, wherein this is RF heating, and this is insulation chamber. In this we keep all these things, and powder and seed attachment. So basically it is one experiment takes 4 stages: outgassing of your graphite parts, which may carry trapped boron or phosphorus or nitrogen impurities. So we need to carry out this in very low vacuum, say 10⁻⁷. Sorry?
Sir, please complete within 1 or 2 minutes, sir.
Okay.
Sorry to interrupt you, sir.
Okay. Then we need to, basically this purification is required to minimize the impurity levels. Then seed attached by heat process. This is the basic method. Your source powder is sublimed to the bowl. So this is our normal reactor chamber at room temperature and at after 2350 degrees Celsius. There are various parameters we need to optimize, and you cannot optimize one parameter, varying one parameter at a time, because one experiment involves huge cost, say 8 lakh rupees, more than 8 lakh rupees. So if you vary each one experiment at a time, it takes crores of rupees. For that simulation and other process we follow. Sorry. So for that we use design of experimentation, that is DOE, which is a statistical method which gives the opportunity to you to optimize your parameters within a very limited experimentations. For that we consider temperature, pressure, source to seed distance, and coil positions, which are the prominent factors out of those. And we thought of having 3 levels of 2315 degrees Celsius, 2325 and 2335 degrees Celsius, and other parameters like pressure, source to distance. And accordingly we thought of 3 levels. We took 3 levels. So this method is very much useful to optimize and reduce your cost involved in that. So instead of varying each parameter, you may take 81 experiments. So it may take 8 crore rupees to optimize that, but we optimized within 9 experiments. So we carried out 9 experiments, and we found that DOE 6, design of experiment 6 experiment, is very much giving prominent results. So this is the DOE 6 crystal grown, and out of that we cut lap it, polish it, and these are the some of the wafers taken out from this crystal. Of course, these are very having resistivity very high. So we want to reduce it up to 10⁻⁴ or 5 ohm centimeter for using it into hemp devices for defense applications. So for that we use the vanadium carbide doping homogeneously mixed in within the source powder, and but it could not resulted in good crystal. So this is undoped greenish kind of, and this is doped. Although powder is doped, incorporated doping has happened, but could not resulted into the crystal growth. So then we move to the vanadium carbide only. We kept a mini crucible. In that we kept vanadium carbide powder, and we carried out experiment. But if you see, there was no hole into the cap of this capillary mini crucible. So this is the laminar flow of old grown crystals. And due to keeping this mini crucible, we can find out disturbances over there. So due to that, we could not achieve the proper results. Then we thought of having 3 holes to escape vanadium species. So we took vanadium foils, and we added silicon carbide powder into that, and again we added silicon carbide powder surrounding to that, and then we got laminar flow, and due to that we got prominent result. So you can see this is the vanadium doped Si6 single crystal. This is previously undoped. So greenish color comes with because of unintentionally doped nitrogen. So this is N type giving greenish result, and you can see this brownish color due to this vanadium doping. So these are, we hope this is our target is to achieve 10⁻⁵ ohm centimeter resistivity, and we are hoping that it will cross more than 10⁻⁵, and efforts are underway to again shoot up the resistivity. So thank you so much, and this is our team, our director, and Sandeep Mahajan, principal institute, myself. This is our lab. Thank you so much.
Thank you, sir, for such a wonderful presentation and sharing your research with us. Let's have 1 or 2 questions. One question from the audience: what is the how big size, or what is the limit of the dimension that you got the single silicon carbide as a single crystal?
Okay, so basically our reactor dimensions itself limits your crystal growth dimensions also. We can go up to 4 inch, but time being now we are having only 2 inch diameter single crystal we can grow, and if you thought of length, then we can grow up to 15 to 18 mm in thick. So by one bowl we can have more than 10 to 15, in between 10 to 15 wafers. So of course, in market, one wafer you get more than 50,000 rupees.
Okay, okay. Thank you, sir. Sir, I have one question.
Okay.
May I know the purity and percentage of single crystallinity you got of silicon carbide?
Yeah. So before vanadium doping, because after vanadium doping, it is under characterization. But whatever we grown N-type and unintentional dope, so our crystallinity FWMHM is around 20 to 25 in between.
Okay.
So, and in a market availability, Cree is the leading company in this business. So they are having 16 to 17. So a little bit we are nearby to that.
Okay, okay. Thank you, sir. Thanks once again. So we'll move to the next oral presentation, OP4, by Dr. Neeraj Joshi. Dr. Neeraj Joshi is from Karnataka Government Research Center, Mangaluru. I request you, sir, to share your PPT and start the presentation. Dr. Joshi?
Can you hear me now?
Yeah, we can hear, sir.
So
Please share your presentation. The title of his presentation is High Q Whispering Gallery Mode Resonators for Sensing Applications at Terahertz Frequency Range. You can start now, sir.
Yeah, so can you see my presentation now?
No, sir, yet not. We are not.
Oh, 1 second. I'll just. Sure. Yeah. Just a minute. Huh? Share. Now, can you hear? Can you see?
Yet not, sir.
Sorry. Share. I'm not getting that window. I somehow 1 second.
Is there any problem, sir?
Yes. Madam, can I just leave and come again? Maybe some problem is there, I guess. Hello?
Yes, sir. Yes, sir.
Hello?
Yes.
Hello? Can you hear me?
Yes, sir. We can hear you, sir.
Yeah. I am finding some difficulty. Actually, it's not showing. Can I just leave and join again in a second?
Sir,
huh?
by the time, I think we can start the next, and after that.
Okay.
Okay, sir. Okay.
Yeah. Okay. That's okay.
Okay.
I'll find out
Thank you,
at the time. Yeah. Okay.
Next oral presentation, OP5, Dr. Nagesh Bhandari. Dr. Nagesh Bhandari, are you there? Dr. Bhandari?
Yes, ma'am. Just 1 minute, madam.
Yeah. Dr. Bhandari is from PTEA's Babu Raoji Golab College, Pune. I request you, sir, to share your presentation and start it. The title of his presentation is Tin Oxide Nano Composites as High Performance Gas Sensors and Insight to Doping Materials. Yes, sir. We can see your presentation. Now you can start it. Please unmute yourself.
Yes.
Dr. Bhandari?
Okay. So good afternoon, everybody. Good afternoon, everybody. Can you hear me?
Yeah, sir. Yeah, sir. We can
Am
hear.
I
Yeah. You are audible, sir. You can start now.
Yes. Thank you. So one, I want to thanks to the organizers of this for me for my on this national seminar. Okay. So my topic is as a and to so myself is Bhandari working as a professor on good. So basically we know that the concept of sense is not new to human beings because we are different in senses.
Sorry to interrupt you, sir. Your voice is breaking, sir.
Touch.
Dr. Bhandari?
Madam, can I rejoin?
Yes, sir.
Can you see my slide?
No, sir. Yet not, sir. We are unable to see your presentation. Is there any problem, sir? Dr. Bhandari?
Madam, I think he has logged out. He will log in again. We will wait for a second.
Nadargi, sir, shall we start for the prayer presentation?
Shall I try?
Yeah, sir. You can try, sir.
1 second. I'll just share it. Okay.
Is there any problem
Bangi
with you,
madam?
sir? Yes, sir.
It seems the network issue with both of the speakers.
Yeah. I think
Neerav Joshi is now
sharing his presentation, sir. Right, sir?
okay. So we will continue with the Neerav Joshi, sir.
Yeah.
Can you hear me now?
Yeah.
Yes.
Yeah.
And can you see my video here?
Yes, very clear. You can go ahead, Neerav Joshi, sir.
Okay. So I'll start now.
Okay.
Right. Fine, sir.
Can you see my slides here?
Yeah.
Correct. We can see it.
Okay, so I'll just zoom in so that you can see clearly. Okay. Yeah. So, sorry. Yeah. So I will talk about some of my work of biomolecular detection using terahertz range frequencies. And this is the device is a whispering gallery mode, which is not very old. Which is not very old actually. So let me start with the whispering gallery mode. What it is. So in 1910, Lord Redlich has studied this phenomenon and explained. So in which in the South Paul Cathedral in London. If you see here, this is a circular geometry of the cathedral. Here, if someone whispers something, that whisper can be heard back again, and that sound travels through the circumference of the cavity, and you can hear it again. And of course, with some conditions there which need to be satisfied. So this phenomenon he observed. And this was in acoustic range. So see here, you see the people are sitting here, and when they whisper, they hear themselves again back. So with these conditions, so condition is that the wavelength of the sound waves should be integral multiple of the path length. So basically circumference of this cavity. So and other conditions also, of course, materials and the material of the cavity and other things. But see, so this observations people have studied in different electromagnetic radiations also, like optical range and other electromagnetic radiations. And they have found the similar effect in the other frequency range also. So what he said that when this any wave propagates, it undergoes decay, and that decay is proportional to 1 by r square. That is inverse square law. But when this radiation or any frequency propagates in a whispering gallery mode in a cavity, closed cavity, it follows 1 by r law. And this reduce in the wave dissipation gives high density modes, which are confirm in that particular cavity, provided the other conditions should be satisfied. So this is what he observed, and many people have studied this phenomenon in other frequencies, light, optical range, and other frequencies. So, so what are the main component to define this kind of phenomena? Is first is the electric field component, polar electric field component. Second is radial electric field component, and which is in fundamental mode, and azimuthal electric field component. So these are the three main parts which define this phenomenon. Now I will talk about something about terahertz frequency also. So terahertz frequency lies between infrared and microwave range in the electromagnetic spectrum. If you see, so here, so like 0.1 terahertz to 10 terahertz, roughly this range is called terahertz range. Of course, it's not very hard and fast rule that, you know, after beyond 0.1 terahertz is not a terahertz. But yeah, generally this frequency range considered as a terahertz frequency range, which correspond to wavelength of 0.3 millimeter to 3 millimeter. So it's a millimeter range radiations. People are using this terahertz in many applications like spectroscopy, scanning, and short range communications, and etc. But the problem with this terahertz is that their generation, that is source, and the detector is not very well developed field actually. So okay, now recently there are many other, you know, development has done and got some good terahertz sources. So the main problem is to get the high power terahertz. So one can generate like nano watt or a few microwatt of terahertz radiation, but to generate higher, it needs more development, which is still underdeveloped field actually. So, but still, application-wise, people worldwide using this terahertz for many applications. Here we have used for biomolecular detections. And why we have choose this radiation? Whether people have using like optical range also, which has very high power, and one can get very good sensitivity also, up to 10 to the power 10. They have reached but the problem is they are very hard radiations. So if you use in biological samples, so they ionize the the sample, and that is the main problem. But terahertz, they are non-destructive radiations. You can use it for biological samples also without destructing. So this is the main advantage of the terahertz. Now, so what experimental setup we have used is here in this schematic diagram. So basically, terahertz, as I said, the source and generation is not very much developed. So people are using indirect way to generate these terahertz frequencies. So in which they have the laser, they are using two laser. So with a little bit offbeat phase, and then they generate this output, bit generation. This envelope of this frequency, which is generated by these two frequencies, is in terahertz range. And this terahertz range frequencies then amplified and fed it through here, and then it goes to the sample, and then we do some other mechanism which detect the biomolecules. So what that mechanism will follow. Before that, one has to do simulations to find out the conditions to propagate this terahertz into the waveguide, which carry the radiation, and the whispering gallery mode, which is in our terahertz range. The whispering gallery mode, the size of whispering gallery mode is like in millimeter range, because wavelength of the terahertz itself is wavelength. It itself is in millimeter range. So we need the structure of whispering gallery mode in millimeter range, and then we have to find how the terahertz propagates into the waveguide, how it interact with the whispering gallery mode, and all sort of things. First, we have to simulate. So this propagations, this is the typical equation, Fresnel law, which gives you how the radiation guide through the material. And then we have to see the lot of other things. These are like losses we have to take into account in our equations or in our simulations, which gives what are the losses and the finally Q factor. So when we detect something, we have to have very good Q factor, basically sensitivity of the device. So that need to be comparable. So that we have to find. So all this simulations work we have done, which is very I mean, which will if I cannot explain here, I will just give you the some flavor of it, and I will show you some results. So we have done this simulation in the COMSOL software, COMSOL platform, and in multiphysics module. So here you show, here you can see there are different these are the whispering gallery modes, and we have faded with the different frequency range of terahertz. And then satisfying all the conditions, we have found that the Q factor is like 10 to the power 4, around 10 to the power 4 to 10 to the power 8. It goes up to, in certain condition, 10 to the power 8. And at this particular frequencies, say like 64 and 67 and something, the gigahertz. So in this frequency range, they are giving this kind of Q factor. So these are the results, like after so many results, these are the selected results we have choose for our geometry and our waveguide. This is the setup of terahertz spectroscopy setup. This is in photon group in TIFR. We have mounted this, and this is actually enclosed in a plastic cover and with the nitrogen flow, because terahertz is very much sensitive to the water actually. So once water comes, then it get absorbed into water and then it destroys. So we have to avoid moisture basically, and we have to control the humidity also and temperature. So it should be very controlled experiment, and this is the only limitation for the terahertz. But still, it will not limit us to do detection, because we can eliminate water peaks coming into the results, which we can filter it out afterwards. So here, what I will show you is a filtration of water peaks, and then what are the signal we are having after detection. That I will show you. So yeah, so this is the you see this is the raw this red dot, no, this small. This is our whispering gallery mode. This is roughly around 5 mm of size diameter. Okay, this is a highly polished ruby actually, and here this white line here. This is the waveguide, and this is a polyethylene. It's a basically plastic high density polyethylene, and in which our waveguide propagates. And what happens is, when it propagates, at the surface there are evanescence waves which generates, and that evanescence wave coupled with this ruby WGMR, and then it gives in the resulting in the detector other side of the waveguide, you see there is a loss of some frequencies which is absorbed in this WGMR. This is circular WGMR in which it gets absorbs and then circulates in particular conditions, particular frequency, which will resonate here. And that deep we can see in the output. So here, this is the simulation what we have done. So at particular conditions, at this gigahertz frequency, we are getting 10 to the power 4 Q factor. And this peak you see here, this is the sharp peak, which says that we have coupled the waveguide with the WGMR. So, and now we have put one molecule of R6G. This is a dye, basically organic dye molecule we have introduced on the WGMR here, on the surface of the WGMR here in this side. So, and then because of this, what happened is the resonance frequency which is resonating here into the ruby, its path length will change because of this, and its optical behavior will also change, and that change we can see it in here. So this is the see, this is without any LRI, without this is without any WGMR near to the waveguide, and then we come closer to the waveguide, we see some peak which shows that we have coupled the WGMR with the waveguide. And then as we vary the concentration of this dye R6G, we see there is a change in the peak full width half maximum, plus it is shifting also. So this shows that this corresponds to the different change in the ppm level of the this die. Same way here, we can now this is the sensor device, so it should be there should be tunability also. Ideal device must have tunability.
Dr. Joshi.
So here we have checked the tunability. Here we have varied the refractive index of the coating material on the WGMR, so as to see whether it can give the tunability or not in a different frequency. So yes, we are seeing the change. As you change the refractive index here, these peaks are shifting, and this shift is correspond to roughly around 100 megahertz. So in megahertz resolution, you can see the change. So from gigahertz to the megahertz. Now, second thing is that if we change the coating layer thickness, this is other method. If we change the coating layer on the WGMR, whether we can see any change or not. So we have seen here, so different with the different thicknesses, 2.5 micron to 10 micron change. We have seen this. This is a huge change from 640 to 650. So this way we can tune also our WGMR device. Now, so so now this is overall picture actually. Here you are seeing there is a laser here, this laser which is amplified and fed here into the waveguide. And then when this WGMR, this circular cavity you are seeing, that is the WGMR, which comes into the vicinity of the evanescence wave of this waveguide, some of the frequency get absorbed inside it and then start resonating. And that resonance, that deep into the frequency which is absorbed here, you can see in the output detector, as a deep. Okay, so this frequency has got absorbed, this first one. And then when one particle in a molecule, even single molecule come on the surface of this WGMR, you see, sorry. So that will change its path length, which is resonating inside, and then you will see the other shift in this dip. So this shift and this particular frequency at which it get absorbed, that is a signature of this particle. So this way we can say, okay, so and so particle has detected. So this is what the detection method works, and one can change the its tunability and its its thickness, and then so as to detect the other molecules. Now the terahertz waves, they are like their frequency matches with the vibration and rotational spectra of the many molecules. So like biomolecules, bioproteins, or even explosives, all these molecules has the same vibrational spectra. So which can get absorbed and which absorb this terahertz, and then they give a very specific signature. So detection of all this material can be possible with this terahertz. So these are some publications, and I would like to thank my photon group at TFR, Prabhu sir, Venugopal sir. They are the pioneer in the photonics. And in IIT Bombay, we have done simulations. All the simulation has been done there under the Datu Gupta's lab. And CG Mithai, she was my PhD student. Now she just completed her PhD. And of course, our German collaborator in Max Planck Institute, they are having the similar setup as the photon group in India. So, and they have the same system where we have worked also. And from my college, my student Arjun Rao, he is also now going to complete his PhD on this topic. And in Mumbai University Nano Center, master students, they also have came for their internship program. And all this happened with all our members. And of course, not least, DST has provided us 58 lakhs of funding for this project to detect the myomolecules. And which will be complete in very soon time. Yeah, thank you for attention.
Thank you, sir, for such a nice presentation. Now we will move to the last oral presentation of this session by Dr. Nagesh Bhandari. Dr. Bhandari, are you there? Dr. Bhandari, can you hear me? Dr. Bhandari? Dr. Bhandari is from PDA's Babu Raoji Golab College, Pune. The title of his presentation is Tin Oxide Nanocomposites as High Performance Gas Sensors and Insight to Doping Materials. I request Dr. Bhandari to share his PPT and start the presentation. Dr. Bhandari, can you hear me? Are you there, sir? Dr. Bhandari? Sir, we can see your presentation. You can start now. Dr. Bhandari, can you hear me? Is there any problem, sir? Sir, is there any problem? You're not audible, sir. Sir, we can't hear you, sir. I think there are some internet issues with the Dr. Bhandari. He is trying to share his PPT. Just wait for 2 minutes. Let's see. Sir, you are not audible to us. And your PPT is not visible to us. No, it is audible, sir, but we can't see your PPT. No, again, you are not audible, sir.
Bhattacharya sir.
Screen not visible. He is not audible. Now we can see your screen, sir. Please start your presentation now. Nadargi sir. Nadargi sir.
Yes, madam. Madam, what we will do, since I think the internet issue is there with him. So if time permits, then we can take this oral presentation at the end of the session. So we will continue with the timetable. So let's have a lunch break for 15 minutes at 3 a.m. 3 p.m. we will start with the rehearsal lectures. And after the 2 lectures, if time permits, we will ask the oral presenter to give the presentation. So we will have a short break of 15 minutes now, and then we will
before that I want to say, before that I want to before stopping, I want to say a few words. So congratulations to all the presenters and thank you for the nice presentation. Finally, on behalf of School of Physical Sciences, I thank the keynote speaker, Honorable Professor P.S. Patil sir, and all the oral speakers to be with us for this virtual event. Thank you all. Now we will have a short lunch break of 10 minutes and we will gather back sharp at 3 p.m. for the next session, which will be coordinated by Dr. Tabassum Mujaba. Thank you all.
Nadargi sir. Nadargi sir.
हाँ बोला की सर.
मीटिंग क्लोज करू नका. मीटिंग चालूच असू दे.
हॅलो सर.
हा मीटिंग चालूच असू दे.
एक मिनिट सर. हुळे सर मला ऐकू येईना. एक मिनिट. काय म्हटलं सर?
मीटिंग चालूच असू दे, क्लोज करू नका.
हा मीटिंग चालू राहू द्या. मी ते डिपार्टमेंटचे स्लाइड्स शेअर करतोय.
हा त्या लावून ठेवा. चालेल.
ओके. ओके. येस येस. हो हो. हा नागेश.
Hello, sir. Badru, sir. Hello. Nadargi, sir. Hello.
आवाज येतोय लोखंडे सर तुमचा?
येतो ना? जरा कमी करू का? का असं द्या?
नाही, ओके आहे, ओके आहे.
लेक्चर चालू आहे. हा, ऑनलाईन. आता लगेच
Lokhande sir, your voice is clear.
Hello? Hello, Nadargi sir?
Yes, you are audible.
Okay.
No, this is correct, sir. एवढंच राहू द्या.
Sir, my voice is audible?
Yes,
Nadargi sir?
Yes, Mujawar madam, voice is clear.
Okay, sir.
Suryavanshi sir?
Am I audible?
Yes, you are also audible. So we will start the session. So over to Mujawar madam, please continue.
Thank you, sir. Good afternoon, everyone. Welcome to all in the third session of National E-Conference on Materials for Emerging Technologies 2021. In this session, we have with us Professor Dr. B.R. Sangpal from the Department of Physics, VNIT Nagpur. I would like to welcome him. Welcome, sir. Now, may I request Professor Dr. S.S. Suryavanshi, sir, to kindly chair this session. I over to Dr. S.S. Suryavanshi, sir. Please, sir.
Good afternoon, everybody. Thank you very much, Dr. Mujawar. Now, we will proceed with the session. To start with, I will just give the short introduction of Dr. B.R. Sangpal, sir. B.R. Sangpal, sir, is a professor in Department of Physics, Vishweshwara National Institute of Technology, VNIT Nagpur, which is an institute of national eminence. He is working as a Senate member of VNIT and served as head Department of Physics and chairman BOS Physics Department for 2 years and associate dean exam for 2.5 years for VNIT. As HOD Physics NIT, VNIT, he has successfully received DST Feast grants of 219 lakhs. He was nominated for Shanti Swarup Bhatnagar Award in 2018 by Director VNIT Nagpur. After obtaining his PhD from Shivaji University, Kolhapur under the guidance of Professor C.D. Lokhande in 2001, he worked as scientist, Helmholtz Center, Han Metzner Institute, Berlin, Germany, JSPS postdoctoral fellow, of Guelph University, Japan, and Research Associate at University of Wisconsin, USA. He is the recipient of the Young Scientist Student Outstanding Award for Presentation Award by Material Research Society, Japan, in December 2005, and by Department of Science and Technology, Government of India, to participate in the meeting of Nobel laureates in Lindu, Germany, 2001. Now he has published over 135 publications with H-index of 36, having citations about 3,800. He has guided 13 PhD students. Dr. Sangpal completed 9 research projects with an outlay of rupees 212 lakhs from DST, SERB, DA, BRNS, and UGC funding agencies. He is serving as expert of committee member of AICT and NAC. He visited abroad various countries like Sweden, France, Switzerland, Holland, Belgium, USA, Germany, and Japan for delivering invited talks and attending meetings. He is a fellow of Maharashtra of Academy of Sciences, member of Institute of Physics, UK, the Indian Science Congress Association, Indian Association of Physics Teachers and Materials Research Society of India. His research expertise include synthesis of nanomaterials, quantum dots, nanowires, and nanotubes of inorganic semiconducting materials by using simple and low-cost chemical routes towards device-grade developments such as solar cells, sensors, and supercapacitors. Now we have such a wonderful personality with us today for the Materials for Emerging Technologies 2021. Now his talk today will be on materials mutualism concept, design and development of flexible solid state device grade supercapacitors. So I request B.R. Sangpal sir, Dr. B.R. Sangpal sir, to please start with this session. Thank you very much.
Thank you very much, sir. Am I audible?
Yes, you are audible, sir.
Yeah, thank you very much for this nice introduction, sir. And I wish to thanks convener of this National E-Conference on Materials in Emerging Technology and Director School of Physics, Shlok Ahilyadevi Holkar University, Solapur. So you have given me a chance to present my research work from my group. So first I can share my screen. Screen is visible, sir?
Yes, sure.
Okay.
Please proceed, sir.
Okay, thank you very much, sir. So I made the title called Material Mutualism. That is the one concept it is there, right? So to develop this supercapacitor, which are a solid state supercapacitor, and here I want to give emphasis to synthesize the material, characterize the material, but it is not restricted to that, but we have applied this material for energy storage application, that by means of supercapacitor. So I belongs to Vishweshwarya National Institute of Technology, and our institute is a national institute that is having national importance, and it is a central government autonomous institute funded by MHRD. So we have 3 major branches: engineering, architecture, and basic sciences. After 12th, students, those qualify this JEE examination, they are entering in our institute for their BTech degree. So we have different branches, that about 10 branches are there, and where the students pursuing their BTech. Also we have MTech as well as a PhD, and from basic sciences we have physics, chemistry, mathematics for pursuing the MSc degree through those who have qualified the JAM examination, and also PhD in engineering as well as the basic sciences, and minimum qualification is there, that is GATE and NET examination. So we are providing fellowship to MTech student as well as the PhD student, and they are serving as the institute fellow. Also we have humanities department. So energy storage, here I wish to give the emphasis, which is a new technology which are having wide applicability in various fields. As many researchers, they have developed the energy conversion devices by means of solar cell, where light it is converted to the electricity. But there is an equally important aspect, it is there to store the energy. So this is a one energy storage device. device it is there where we can store the energy by means of supercapacitor. So supercapacitor, it is an electrochemical energy storage device which is having higher energy density than the ordinary capacitor and power density than the batteries. So energy means what? It is the capacity to do the work, and power is how fast the energy it is delivered. So here present emphasis it is given, and many research are working to improve this energy density so that we can replace the battery. Because as you know that this battery, it is having incorporation of the liquid which are toxic, like acids are there, and also this battery are capable up to 3 to 4 year maximum. So you have to replace the battery. So in order to replace that one, people are trying to improve the energy density by means of supercapacitor. So it is possible that in future we can use only supercapacitor instead of batteries. So whenever we are thinking about the supercapacitor, how it is different than the capacitor and the battery. Am I audible, sir?
Yes, sir.
Okay. So we can differentiate on the basis of different parameters, and this is very helpful for the young researcher, young budding scientists, so that they can adopt these methodologies for their future trend. Means not to just synthesize the material, but they can apply for device grade application so that it is directly beneficial to the society. Just in the morning, Professor P.S. Patil sir talked about the fibers, textile fibers, where we can make the nano inside the textile fiber so that it can be widely applicability for the society. So similar thing it is there called as an energy sector where we can store the energy. So here, what are the parameter it is concerned? That is the charging time. So whatever charging time it is there, it is just midway between the capacitor and the battery, because battery requires about some minutes to some hours to charge, whereas capacitor it can charge within millisecond to microsecond. But the supercapacitor can charge within some second. Similarly, the discharging time it is there, which lies between the capacitor and the battery. So most important thing is that energy density. So energy density of the supercapacitor it is about 1 to 10, and it is lesser than the battery. So people are trying to achieve the energy density that possessed by the battery. But the capacitors are there which can charge very quickly and discharge very quickly. That's why it is having very less energy density. Oh, but whenever we are considering about the power density, capacitors are having very wide power density, and supercapacitor it is midway between the battery and the capacitor. On contrary, if you see the life cycle for the battery, it can stand up to just I mentioned, it is for 3 to 4 years, because it can having cycle that is charging and discharging maybe 500 to 2000, right? But a capacitor it can having wide applicability in terms of the cycle life. It can go above lakhs. So here supercapacitor has to have the cycle life about 10,000 to 1 lakh. So that can be adopted in case of battery if it is possible to replace with the energy density. And the charging discharging efficiency, it is the midway between the battery and the capacitor. Here I have shown the supercapacitor device which is already exists, and this supercapacitor are available in the market where the liquid it is there inside this capacitor. So again, whenever we are using with the liquid, there are a lot of problems are there that we are going to discuss afterward. And this is just a battery it is there, and this is a capacitor. Lot of applications are there for this supercapacitor in various fields, like power devices, like a train, and then maybe cars are there, and then maybe in the bus it is there. And recently here supercapacitor it is used in Shanghai, and also it is used in one car in Pune. One company it is there called Spell Technology. They have used and run their car on the basis of the supercapacitor. But this supercapacitor it included with the liquid electrolyte. So prototype device it is made and it is used inside the battery. So you can see that at one charging port here, bus can charge within few minutes, and then it can travel to the next stop where again it can be charged. So within moving from one stop to the next stop, it can, whatever the supercapacitor it is there, it can be discharged, and again at the port again at the stop it can be get charged. So that is the use, means you have to use this supercapacitor for short interval of time, but not too much long interval of time. But maybe in the future it may be possible by cascading the number of supercapacitor maybe in the series or parallel combinations. So whenever we are thinking about the supercapacitor or any device, whenever you want to make that device, whatever the cost issue it is concerned, that should be very low cost. And the method, it should be easy and accessible. So that easy and accessible means what? For example, if your method it is environmentally friendly and non-vacuum environment it is there, or non-vacuum technique it is there, so it can have a wide application. So method should be easy and accessible. And whenever you are thinking about the raw material which is going to be used for your device, your raw material should be easily available. And whenever you are thinking about the domestic use, people should not think about that much money, because it should be having lower cost along with long-term stability. These are the basic requirement it is there for any device. As we are considering here, it is maybe for supercapacitor. So here, whenever we are thinking about the supercapacitor, to make the supercapacitor, as this components, it is recent trends in emerging technology. As nano, it is the emerging technology. So I made the presentation in the orientation of this emerging technology. So nano can play a very vital role by changing this just particle size. We can tune the properties. Then you can ask yourself whether it is so complicated to work with this nano, and especially for this talk for supercapacitor. So I am working on the supercapacitor gas sensor as well as the solar cell, quantum dot sensitized solar cells, nanowire based solar cell. But here I am consulting about the supercapacitor. So just I am restricting my talk for the nano for the supercapacitor application. So whenever we are thinking about the nano and it can be embedded inside the thin film form, there are two approaches are there whenever you are thinking to have to work on the nano material. The first approach, it is called top-down approach, and the second approach, it is called as a bottom-up approach. So in the top-down approach, you have to use either crushing, grinding, milling, it is there, but you cannot go beyond a certain limit, under the certain limit, because again, you have to control the size of the particle. It is also a problem. But whenever you are thinking about the bottom-up approach, which is called as a solution chemistry, that where you can utilize this bottom-up approach to control at the certain level, so that you can grow up from bottom to top, so that desired morphology, desired thickness, it can be attained by using this approach called bottom-up approach. So here, I am concerning about the chemical method, how it is beneficial for this bottom approach to synthesize these nanomaterials. So whenever we are thinking about this chemical method, it is versatile and it is simple, low cost, and it is controllable, because whatever the basic building blocks are there, these are ions. So it is possible to control at the ionic level or molecular level. So here I am concerned with the certain deposition technique like chemical bath deposition, sealer, deep coating, Dr. Bell techniques are there. So these are some simple low cost techniques are there and possible for the integration for large area. And that's why it is possible to integrate for the industry. So it is scalable to the industry. And the most important thing is that it is non-required vacuum environment. So the cost issue can be reduced drastically. So here I am considering about the nanomaterial which can be made by using simple solution chemistry for the supercapacitor application. But whenever you are thinking about any device level application, you have to synthesize, you have to characterize, and then you have to apply, and so that the property can be tuned. But you should have the background about the chemistry as well as the physics, so that whenever you are thinking to make the device, but whenever you are going for the industry, you should have the technology background as well. So here, whatever the supercapacitors are there, basically this can be categorized into two category. One, it is called as a EDLC type supercapacitor, and second one, it is called as a pseudo type capacitor. This EDLC type supercapacitor, where the storage mechanism involves the charge separation at the electrode electrolyte interface, and most of the carbon materials like carbon nanotube, that is multi-wall carbon nanotube, single wall carbon nanotube, graphene, reduced graphene, activated carbon, this can be used for this electrical double layer capacitor. Where in the pseudo capacitor, periodic reaction of the surface species gives rise to capacitance, and most of the metal oxides, metal chalcogenides, polymers, this can be used for the supercapacitor. Am I audible, sir?
Yes, sir. Yes, sir.
Okay. So here for the EDLC, the surface area reaction, it is there, but it suffers through the low capacitance. But on contrary, it is having very high stability. But here, if you are thinking about the pseudo capacitor, as this is a periodic reaction, it is there, and surface species are involved. So surface and bulk reaction, it is occurring, so that it is having high capacitance, but it suffers through the low stability. So here, if you have this supercapacitor, which is EDLC and pseudo, that can be categorized like a carbon aerogel, carbon nanotube, conducting polymer metal chalcogenide. As this EDLC, it is having its own advantage and its own disadvantage, and pseudo materials, it is having its own advantage and disadvantage. If you combine this approach to have the hybrid capacitor by combination of EDLC with the pseudo, and that's why I have given the title as the material mutualism. So we have to take the benefit of each. For example, from EDLC, we have to take the benefit of the high stability, and from the pseudo, we have to take the benefit of the high capacitance, so that we can have the advantage of the material mutualism, so that we can form the hybrid capacitor. So here I am considering with the hybrid capacitor, which is the combination of EDLC and pseudo material. As lot of materials are there from the EDLC, like CNT, graphene, carbon aerogel, activated carbon. Here we have used the carbon nanotube, which is a multi-wall carbon nanotube, which is having very high conductivity and high surface area. So advantage of the material mutualism concept, if you are concerning, is the carbon nanotube with high stability and conductivity. And if you are thinking about the pseudo material, it is having high capacitance. So whatever the material mutualism concept it is there, it can have the composite with improved electronic conductivity with well-directed conducting path, so that it can have a dual charge mechanism. But the basic requirement for the supercapacitor, it should have the high conductivity, large surface area, good chemical stability, and good reversibility. So whenever you are thinking about to replace the battery with the supercapacitor, you have to think about the energy density. So whenever you are thinking about the energy density, to increase the capacitance, we should think about the specific surface area, porous size, electrical conductivity, and redox capacitance. And if you are thinking to improve the potential window called as a voltage, we should think about the electrolyte, that is the maybe organic electrolyte or ionic liquids are there, or you have to think about the asymmetric combination where different materials can be utilized for the supercapacitor, where we can enhance the energy density. So here we have focused with the surface architecture, as we have taken the conducting substrate. In the present case, we have taken stainless steel as the conducting substrate, on which we have deposited the nanoflex type morphology, nanoparticles of the metal chalcogenide, metal oxides are there. We have also deposited nanowires. We have also deposited core shell type of nanowires on the conducting substrate. Also, we have deposited carbon nanotube. So in order to have the material mutualism, what we did, we just combine the carbon nanotube and the other material, like maybe in the nanoflex morphology, means carbon nanotube, it is coated with the nanoflex like morphology. Carbon nanotube, which is coated with the nanoparticles. Carbon nanotube, it is coated with the quantum dots, or carbon nanotube, which is coated with the polymer. So we have applied different material to check the possibility whether it is to increase the energy density. For example, this is just the SNSE nanosheet, it is there. It is a pseudo material, and we have used these hexagons of the SNSE nanosheets, which is the 2 dimensions, and we have achieved good results, and that is published inside IEEE transaction of power electronics having impact factor 6. Not only this one, we have deposited carbon nanotube on substrate, and then we have coated with the different material like polymer. Then we have coated with the quantum dots of the zinc oxide, then quantum dots of the TiO2, then quantum dots of the cobalt oxide. Then we have coated with the nanoparticles of the solid solution belongs to the Bi2S3 and PBS. Then also covered with the molybdenum tenorite and also CeO2 on the high surface area carbon nanotube. All these results, which is published inside the journals, and you can go through my Google Scholar so that you can get different ideas from these papers. Not only this one, we have just coated vanadium sulfide on the carbon nanotube, and which is having hexagonal shape on the carbon nanotube, because there is a lattice matching between this carbon nanotube and vanadium sulfide. And there is a cellular method we have used to coat this vanadium sulfide, and we observed there is a hexagons which is grown on the carbon nanotube, and it is published inside the very high impact factor journal Applied Material and Interface. And also we have used cadmium sulfide, and we have anchored with silver mercury sulfide, so that there is a formation of the core shell, and it is also published inside the Nanostructure and Nano Objects journal. So we have done lot of devices based on the liquid cell as well as a solid state device. Here, this is the data for the specific capacitance for lot of materials, as well as specific energy and specific power. And also we have done the solid state device using 2 electrode configuration, that is the sandwich structure, it is there. And also these are the published results, where This is for the potential window, then specific capacitance, specific energy, and specific power. Then among these, just I want to present one case study that is just a vanadium oxide, which is the pseudo material, which is coated on the carbon nanotube. And up till now, this we found that it is giving very highest energy density as well as the potential window. So we have used this one, and for the same, I have just completed one project belongs to the Technology Mission Division, DST, Government of India, in collaboration with the co-PI, Dr. B.B. Kale, that is, he is a director from MET, and one industry partner called Spell Technologies Pune, Dr. Rajendra Kumar Sharma. He is fabricating the supercapacitor for the industrial application, and he has industry for the capacitor as well as supercapacitor in Pune. So my concern, it is the material mutualism between the pseudo-capacitive vanadium oxide with EDLC behave carbon nanotube, so that we can have a dual charge mechanism, so that we can take the benefit of the both in thin film form as the electrode material for supercapacitor application. So how we have coated the carbon nanotube? We have not fabricated the carbon nanotube. We have just commercialized carbon nanotubes are there that we have procured, and we have used simple deep and dry coating technique. So we have made the viscous solution of the carbon nanotube by using probe sonication, then functionalization, different things we have done. Just we have taken the stainless steel, which is a flexible substrate. So we have dipped inside the carbon nanotube, and then we found that this carbon nanotube very uniformly coated on the stainless steel substrate, and we have dried that sample under IR lamp, and we have optimized that with number of immersions. And this is photo shows the carbon nanotube that we have optimized with the different substrates like FTO, PET, glass, stainless steel, and PVC. So depending upon the whether substrate surface it is hydrophilic, hydrophobic, right? Surface area activation it is required, electrochemical activation it is required, surface passivation it is required, nucleus center formation it is required, depending upon the type of the substrate that you are going to utilize. And this is just a carbon nanotube. Here you can see the scale bar, it is 300 nanometer, where this carbon nanotube, which is conducting carbon nanotube, these are uniformly covered with a very high surface area, that is interconnecting nanowire connections are there, which can be used for anchoring vanadium oxide on the outer surface area of this carbon nanotube. And this carbon nanotube, it is having EDLC behavior, and vanadium oxide, it is with the pseudo material. So we have used simple chemical bath deposition technique, and we have just coated this vanadium oxide on the surface of carbon nanotube just at 60 degrees Celsius. So this technique, it is also simple and low temperature process, and it is possible to integrate for large area as well. And we have confirmed through the XRD studies that whether vanadium oxide it is coated on the carbon nanotube or not, that is through the structural identification, where we observed orthorhombic structure of V2O5. This is the carbon nanotube. You can see with the different scale bar, it is there. So here you can see that this is carbon nanotube. This is vanadium oxide, which is just coated on the stainless steel, which is having flakes-like morphology. And this is a vanadium oxide coated carbon nanotube. And these are the vanadium oxide flakes of the vanadium oxide flakes, which is coated on the high surface area carbon nanotube. And here the basic requirement, as it is having higher conductivity because of the EDLC carbon nanotube, and vanadium oxide, it is a pseudo, so that it can provide very high surface area on the carbon nanotube. So dual charge mechanism, it is possible to achieve inside this one. So this is a TM image where you can see that this is a flex, and here you can see that this is 50 nanometer, this is 20 nanometer, this is flex which is covering on the carbon nanotube. Also, we have done some EDX mappings to see whether vanadium oxide it is coated on the carbon nanotube or not. And here you can see that different elements like vanadium, oxygen, and carbon it is there, which is the confirmation that vanadium and oxygen it is covered on the carbon nanotube. Am I audible, sir?
Yes, sir.
Okay. So here initially we have tested this one with the liquid composition using single electrode in 3 electrode system, where vanadium oxide coated on the carbon nanotube we have used as a working electrode, then AgCl as a reference electrode, and platinum wire as a counter electrode. And we have used a potentiostat, that is Parstat 4000 from USA, for this measurement. So initially we have tested with just carbon nanotube coated on the stainless steel, then vanadium oxide which is on the stainless steel, and vanadium oxide coated on the carbon nanotube. And surprisingly, you can see that when we have done with the vanadium oxide which is coated on the carbon nanotube, it shows very high capacitance as compared to the single just carbon nanotube and vanadium oxide. We have checked that one with respect to the scan rate, and we observed very high specific capacitance about 1238 Faraday per gram at scan rate of 2 millivolt per second. And this is the formula that we have adopted for the calculation. Then also we have done some charge discharge studies and also specific energy and specific power calculation. Specific means what? Depending upon the amount of material it is going to be deposited on the substrate surface. And specific capacitance from the charge discharge study, we observed it is 160 Faraday per gram at 1 ampere per gram, and very high specific energy, about 72 watt hour per kg, by consuming 2.3 kilowatt per kg, that is the power density. Then also we have checked the stability of this cell by repeating the CV cycle, that is by charging and discharging, and we have run this one up to the 4000 cycle, and here we can see that this is stable up to 93% for 4000 cycle. But here there is an issue with this liquid state devices where liquid evaporation may be there, imperfect sealing it is there may be there, interaction of the liquid with the substrate may be there. So whenever you are using these liquid devices for long term, that is having stability issue. So we thought to make the complete solid state device, and we have used simple 2 electrode system which is sandwiched for this one. And as you can see, this is the industrial benchmark, it is there. These are the different companies working on the supercapacitor where they are using liquid state device where electrolyte it is there. So it can cause the long-term issue as well. We have thought to make the solid state device because no industry still it is working on the solid state device. And here for the making the solid state device, we have used 2 electrode, which is stainless steel, which is coated with the vanadium oxide layer on the carbon nanotube. This is the one electrode it is there, and then another electrode, the same electrode it is there. And these 2 electrodes are sandwiched by using gel electrolyte, and this gel it is prepared by using conducting electrolyte, that is LiClO4, in the non-conducting matrix, that is the polymer which is called PVA, that is polyvinyl alcohol. So this is a dielectric which is there, which is used inside this 2 layer, and this is the conducting matrix, that is the conducting channel between these 2 electrodes. And this both electrodes are similar, that's why it is called as a symmetric device. And we have used vanadium oxide coated carbon nanotube as both the electrode. And here you can see the stepwise development. This is carbon nanotube, then we have covered with the vanadium oxide, then we have covered with the gel, and then we have sandwiched together, and then it is formed the complete symmetric solid state device. And we have dried this one for complete drying of the gel electrolyte, and then this forms the complete flexible solid state supercapacitor. And this is the area that we have done 3 by 4 centimeters square. So we have checked the potential window of this one. As you can see that for the liquid, it can use the voltage window about 0.9. But whenever we have made the device just a symmetric, not asymmetric, just remember, it gives the potential window of 1.8 volt. And we have done with the scan rate also, it gives very high capacitance for the solid state device. Complete solid state device, it is about 468 Farad per gram at 2 millivolt per second. And the interesting fact is that this device shows very high stability, better than the liquid cell, that is 96% at 4000 cycle. It is very, very stable as compared to the liquid device as well. So it is having more stability than the liquid configured supercapacitor device. Also, we have tested with the bending, that is the mechanical bending. We have bent that one up to 175-degree bending angle, and we have seen the stability up to the 90% retention. That is the capacitor retention, means whatever the final value, it is matched with the reference value. And we observed only 10% decrement it is there, even at 175-degree bending angle. Not only this one, we have tested for almost 7 days this device, and it is very stable. We found that it is very stable. And this small device, 3 by 4 centimeter square device, we have used to run the V90 panel consisting of 21 red LEDs, and it was run up to 60, that is 6 minutes it is there. We have charged this one about 1 minute, and it has run up to 360 seconds, that is about 6 minutes. And this whole result, it is just whenever we have used vanadium oxide on stainless steel, it is published inside the Electrochemical Acta, and we have coated with the vanadium oxide coated on the carbon nanotube to form the complete solid state device, that it is published inside the Nature Scientific Report. And here you can see that this device, it is used to run the LED panel as well as to run fan. And here you can see that this is the device. Can you see the video?
Yes, sir.
Okay. So this device, it is charged by using 3-volt battery for short time. And then we have taken out after charging. And here you can see just we have used Tixo tape just for the sealing because it is a completely solid state device. But if you are using the liquid state device, we need perfect sealing. This is completely solid state device, which is carbon nanotube coated with the vanadium oxide. And here you can see that this is the V90 panel consisting of 21 red LEDs. So by using simple lab solution chemistry, by using nano material, that is nanoflakes of the vanadium oxide, which is coated on the carbon nanotube, you can make the device in the laboratory. It's just not a publication that it is giving satisfaction, but whenever your device it is working for the social application, society application, it is having better satisfaction. Here you can see that this is for the technology mission division. We produced the same device, it is there. This is a fan, it is there, it is device charging. We have charged for short interval of time. Here you can see that it is charged. Now charging it is there, this is battery, it is there. Now it is discharged. Here you can see that this fan, it is running very well with a very high speed. And that is the real satisfaction that you, whenever you are doing any device. So here you can see the fan, it is running well, still it is running. Still it is not stopped. Now you can see that the speed it is now decreasing and now it is stopped. So that is the beauty of this solid state device that you can make in the laboratory for a device grade application. So also this is published inside the Times of India as well as Sakal. And this flexible device, that is lab made device, I showed to VK Saraswatji, that is a member of Niti Aayog, in one international conference where I was invited for this one. And we have given one booth where you can see that Professor Ashutosh Sharma, Secretary TST, Professor Ram Gopal Rao, Director IIT Delhi, they also visited this booth and seen the prototype solid state device that we made in the laboratory. And we also shown that LED panel and also to run this small fan. So finally, I wish to acknowledge TST Technology Mission Division and my project students that they have done hard work to achieve this goal. So we can say that Nano can play a very vital role for energy and environment through the soft solution chemistry. So we can work against the global warming. Thank you very much.
Thank you so much, sir, for sharing your ideas and knowledge with us. Your lecture was very informative and very energetic. Now the session is open for the discussion. Any questions from the audience? I think in the chat box we have two questions. Question 1 is from PK Baviskar. He's asking, what is the stability and life of liquid type supercapacitor?
For example, if you are using from the company, that is the Maxwell company, right, it can work up to 7 to 8 years as well. But you should take care that imperfect sealing it is there, that should not break. But the most of the supercapacitors are using that from the electronic industry. But whenever liquid leakage is there, you have to be cautious that when liquid is coming out from the capacitor, it can damage your whole assembly. So that's why people are trying to replace this liquid with the solid state device. So solid state device capability has to be checked at the industrial level.
I think he got his answer. Now the next question is, are ferritic materials like NiCO2O4 better for battery applications or supercapacitor applications?
Depending upon the type of the assembling you are doing, because although one material is there, it is both the pseudo material is there, but whenever you are depositing that one on what type of the substrate. So whether you are using for the battery, you should have the different substrate like copper or aluminum it is there. Whenever you are using for the supercapacitor, you can use either you can use stainless steel or single copper it is there. So in both the case, it is applicable for the battery as well as for the supercapacitor. But like this nickel, it is better for the supercapacitor than the battery.
Thank you, sir. Once again, thank you so much for joining with us on this virtual platform.
I would like to also thank Professor Dr. S.S. Suryavanshi sir for well chairing this session.
Thank you.
Thank you, sir. Now,
Thank you
let's
very much.
move towards our next talk. Our next resource person is Dr. Shashwati Sen from Technical Physics Division, BARC, Mumbai. Welcome, ma'am. Now, may I request Dr. B.J. Lokhande sir to kindly chair this session.
Let me introduce the research person of this session, Dr. Shashwati Sen. Ma'am completed her MSc in Physics from Devi Ahilya Vishwavidhyalaya.
Sir, your voice is not audible.
Madam. Is my voice is audible now?
Yes, sir.
Let me introduce the research person of this session, Dr. Shashwati Sen. Ma'am completed her MSc in Physics from Devi Ahilya Vishwavidhyalaya, Indore, MP. She joined Technical Physics Division of BRC in 1997 through the 14th batch of BRC Training School. In the initial years of her career, she worked on high temperature superconductors and completed her PhD on the same topic from Bombay University. Later, she started working on various nanomaterials like tellurium, SnO2, WO3 for gas sensor applications. Currently, she is in charge of crystal technology section of Technical Physics Division BRC and working on growth of single crystals and transparent ceramics for their applications in radiation detection. She has received DAE Science and Technology Excellence Award in 2017. Also in 2008, she received DAE SSPS Young Achievers Award. Also in 2008, DAE Group Achievement Award is got to her for her work on gas sensors. In 2014, she also got the award for the growth of single crystals of CSI and NAI for radiation detection. She has more than 200 publications in various reputed international peer-reviewed journals. Also have some patents on her name. She is the referee and editor, co-editor of so many journals. Many symposia she has conducted. Number of PhD students get awarded under her. Also, some are working, and number of research projects yet now she has completed. So, with this short presentation, I have completed the first biodata of Madam.
Thank you so much, sir, for such a nice introduction. Now, may I request Dr. Shashwati Sen, ma'am, kindly to deliver her talk.
Good afternoon, everyone. Am I audible?
Yes, ma'am.
Okay. Thank you, Professor, for my introduction. First, let me thanks Professor Vikas Patil to give me this opportunity to be a part of this e-conference on emerging materials. National conference is there, and I have been knowing him for maybe more than 10 years, and you can say that we both have grown together. We were very young researchers, and then we started collaborating, and our collaboration has given very good results. And today we have also grown, and the process of growing is going on. So with Professor Patil, I have worked on gas sensors, but today what I will be presenting is on radiation materials. So it is going to be a new topic, so I will not tell much, but let me see how it goes. So I'll share my screen, just wait. Okay. So can you see my screen now?
Yes, ma'am.
Okay, thank you. Today I will be talking on materials for radiation detection. So any student can say that why should we study on materials for radiation detections, how it is important to us. So thing is that radiation detection is not really that okay. Let me first say what is the radiation I am talking about. So radiation basically is sunlight, which is very essential to our life, is also a part of radiation. So sunlight we are able to see, and our even sense organs are able to detect it. But when we are talking about sun rays, so it is basically a electromagnetic spectrum. So but it is not so that all the radiations in the electromagnetic spectrum can be easily detected, because as you know, there is x-rays are there, gamma rays are there, which is not visible to naked eyes. And for that we have to have some important materials, some functional materials are required to detect them. So when I'm talking about radiation in my presentation, so I will be talking about high energy photons, electromagnetic photons, which is gamma rays, X-rays, and synchrotron radiation. And also these materials can be used to detect high energy charged particles like alpha, beta, electron, proton, and neutrons. So now point is that these are the photons in the electromagnetic spectrum are at the higher energies. So why how they are interacting with matter, then so that they can be detected. First we should know the underlying physics of detection of this material. So for when we are talking about high energy photons, electromagnetic waves, so we have learned that any photon or the electromagnetic radiation interacts with matter by three processes. First is that photoelectric effect, the second is the Compton scattering, and third, when the energy is higher than 1 eV, basically energy of rest mass energy of 2 electron, then it leads to pair production inside any given matter. So these three phenomena are used for the detection of these high energy photons. And then when we are using a charge particles, detection of charge particle, it is because of Coulombian interaction which happens inside the matter, and which leads to ionization. And neutron also leads to formation of charge particle inside the matter, and then the charge particle is detected. So what is this? The process by which these three I'm talking about, photoelectric effect, the Compton scattering, and the pair production. This is the type of interaction in which the radiation is having with what matter. But then how we are able to detect it? So detection is by a process called the scintillation process. So all the materials which I will be talking in my presentation are all scintillator materials. So what is basically a scintillator material? A scintillator material is a material which gives scintillation process. So scintillation is like when a high energy photon, like here I have taken the example of gamma rays, it is coming and falling and being falling on a scintillator crystal material. It gives out a burst of photons or light pulse which has low energy. Basically, a scintillator material, you can say, is converting a high energy photon into a low energy photon. And this light pulse is a photon of visible energy range, like in the wavelength of 300 nanometer to 700 nanometer. And this is visible to naked eyes. And then you can use photo detectors like photomultiplier tube or silicon photodiodes or other things like photodiodes detectors, which can be coupled to these scintillator materials, and then it can be made to generate an electronic pulse which can be detected. So the gamma rays interact with the host crystal, the scintillator, which causes ionization inside this. So this ionization leads to the formation of electron and hole pair, which are then jump to the electrons then jump to the valency band, from the conduction band to the valency band, and then they migrate to the luminescent centers, and they emit visible photons upon de-excitation. When they come back to the valency band, they give out this visible photons. So this absorption of each gamma ray results in a burst of photons, and these photons are then detected by the photodetector. So this is the scintillator process, and the material for which this gives the scintillation process is called the scintillator. And then, as I was saying, why we have to detect these radiations. So why it is important? It is not only important for the nuclear industry. The nuclear industry means this nuclear reactor and all those people. But these radiation detectors are also important for safety and security of people. So safety and security is one thing, is security because nowadays, because of nuclear proliferation and all those things, there is a lot of smuggling of uranium or other radioisotopes. That is one you need to detect them. Then secondly, it is used in safety like when it is used in X-ray diagnostics are there, that is medical part, but also like baggage scanner. So you must have seen baggage scanner in airport, or even nowadays in malls and cinema halls also, and even in railway stations we have got this X-ray baggage scanner. So where the baggage is being scanned to see what is there inside the suitcase. So this baggage scanner is because there is a X-ray. So they are, for the detection of the X-ray, these scintillator materials are there. Third is this medical diagnostics. So X-ray radiography is a normal, this X-ray which you have always done when you have a fracture or something like that. Chest X-ray is being done very regularly for our COVID cases. So that there is where, because you are taking the X-ray, so you have to detect the X-ray which is passing through the body. So there you require detection of X-rays. Then there are other medical diagnostics like computed tomography, CT it is called, or PET, positron emission tomography, which is required to see inside your brain or the working of heart and all those things. So here you have got a X-ray source like in CT, or in PET you are given some radioisotope medicine, and then it gets accumulated inside your body, and you have to find out like any tumor is there in the body and all those things. So here also you have to use radiation detection. And then there are high energy physics experiments are there. So in nuclear experiments in classroom also we do this MCA, multi-channel analyzer, to detect various radiations. So in high energy physics experiment like in CERN and all, so you require a radiation detector. And then there are other like petroleum industry, whether there is oil or not, and so and so forth, these are used. So this is like I said, this is safety, and this is the cargo scanner, because now if you know that for in every port when any shipment is coming, so you have to see what is there inside the shipment. So there has to be this is the cargo scanner. So they irradiate it with X-rays and then see what is inside the trucks, because you cannot open everything. And this is the baggage scanner, and this is medical. So these are the applications of radiation detector. So what we know now that why we have to detect the radiation, and we have to use the scintillator material for the radiation detector. But what is the scintillator material? What should be its specification? So it should have very high yield per MeV. So what does this term means? This term means that high yield means when 1 MeV of gamma photon is coming and falling on a scintillator material, it should give very high, large number of light photons. Means the low energy photons, it is not that one gamma photon whenever it is coming and falling on a scintillator, it will give one light photon. No, it has to give very high yield. So like generally for materials which are used in nowadays commercially, or which are the emerging materials, they give out like 40,000, 50,000 photons per 1 MeV of gamma photon. So if a gamma photon is coming from a source of like cobalt 60, which has got 1 MeV, so it will give rise to 40,000 photons. So that is one thing. That is one specification which is very important. Second is fast decay constant. Fast decay constant means when like a gamma photon has come, it has fallen on the scintillator, and then it has given out the burst of photon. But this burst of photon should die out fast, so that if there is another gamma photon coming and falling on the scintillator, it should be able to detect that, because there should this process should be very fast. Otherwise, what happens, when one photon comes, you are able to detect it, but the next photon is coming and then it is giving to a burst of light photons. But if the earlier photons has not died out, then this will get merged to the earlier photon counts. So there will be a overlap. So first thing is that you are not able to distinguish between the two gammas which has come in. And then if you are doing like some imaging applications, or there is a very high count of those, so then you will get a afterglow, that is called afterglow. So even you are seeing the effect of the first gamma photon when another gamma photon has also come. So this is not a desirable property, so it should has very fast decay. Then third is high density. The material should has very high density. So why we require high density? Because as in the first slide we have seen that it is the three interaction processes by which this interaction of the high energy photon is taking place, which is the photoelectric effect, the Compton effect, and the pair production. But for this interaction, the material should be having high density, because it should be able to stop the high energy gamma. So it is a normal knowledge that gamma is generally stopped by lead. So why lead is used? Because it is high density, high Z. So so that's why even for detection, we cannot use lead because it is an opaque material. But something of very high density you have to generally use for this. Then linear response comes. So linear response is basically this, the first point only, high yield per EV. So like 1 MeV gamma photon is giving say 40,000, then 2 MeV gamma photon should give 80,000, and 500 keV should get 20,000. So that is the linearity. This linearity is required because this property of scintillator material is also used to detect the energy of the incoming gamma. So if you know the calibration of how much for a given material per 1 MeV gamma, how much is the output yield, you can find out the energy of the incoming gamma radiation. And it is very important because when you are working in high energy radiation experiments or in reactors on all, so you need to know which kind of gamma emitter is there. And because every gamma emitter has got its own signature energy, so if you can distinctly find the energy, you can find out what is the gamma emitter. So that's why linear response is a desirable property, I would say. Then good mechanical property and inert nature, because when you are putting it into say a cargo scanner or say a baggage, x-ray baggage, so x-ray baggage you can put it in airport also, you can put it in a mall also, and you have to put it in a railway station also. So it has to work in all the condition, and it should work similarly at Sholapur as it should work in Srinagar, or it should work in Vishakhapatnam. So it should have, that's why, very good mechanical and property and inert nature. And then obviously low cost has to be there, because it has got so many application for the day-to-day life. And radiation hardness is that whenever gamma is falling, so after many years also, because of gamma there should not be any damage causing because of the incoming radiation. That's why it is called radiation hardness. So these are the for applications, scintillators should have these properties. But as we know, as in all material scientists know, that no single material can have all desirable properties. And that is why, because of this only, we material scientists exist. There is so much research in materials, because not we are trying to find that one single material which will be able to fulfill all our needs. But that is far away to come, and so the research continues. So I will give you few names of these materials, scintillator materials, which are generally used. So cesium iodide and sodium iodide are this cesium iodide, thallium doped, and sodium iodide, thallium doped. So these are very old materials. These are not new materials, but in my presentation, I will show you like how emerging material. I have this cesium iodide thallium, which is a very old material. With our research, we have made into a emerging material. How by tailoring or doing some changes in its property and all. Old material can, with different applications, we can make it a emerging material. So these are two new, but strontium iodide doped with europium, lithium fluoride, calcium fluoride. These are some new scintillator materials. Then yttrium aluminium oxide. This is YAG, not YAG. Huh? YAG is a Ledger material. Similar to YAG, this is yttrium aluminium perovskite doped with cerium. Then lithium borate. Then gadolinium, gallium, aluminium oxide. So these are very big names, you will say. But these are scintillator materials. And the activators are very important in this case. So I will be, in my presentation, I will be talking about cesium iodide thallium dope and this gadolinium gallium aluminium oxide at the end. So this is how it looks, these material. So here I am showing all the photographs of like crystals. This is lithium tetraborate, lithium gadolinium borate, gadolinium gallium oxide, yttrium aluminate, and lutetium silicate. So these are all materials all in single crystal forms. And here calcium fluoride and aluminium oxide doped with carbon. These I am writing as optically transparent ceramic. So why, first thing is like why I have shown all the crystals. So is it that the scintillators has to be in the crystalline form? So yes, that is true. The answer is that when you have to use this scintillator for detection of gamma rays, conventionally it was thought that it has to be a single crystal. So why it is so? So why it is so is that a single crystal has got this ordered structure. So because of this ordered structure, say this is the molecule and this is the dopant. So like I am talking about cesium iodide doped with thallium. So I have got this cesium iodide matrix and doping is very less. So I have got just 3. So what is the role of dopant which it plays in case of scintillator? Basically, a scintillator is a wide gap insulator material and it has got very wide energy gap. Because of the dopant of this, like thallium in this case, or sometimes cerium or europium, I was saying, because of this, they make energy levels in this forbidden energy gap. And this, from this level, we are actually getting the luminescence. So what happens when a high energy gamma photon is coming, the electron jumps this energy gap and then they de-excite and come to the energy bands which is created by the dopant atom, and from there they de-excite, and because now the energy gap is less, so they are, when they de-excite, the photon which comes out is of a lesser energy which is in the visible region. So basically this is the scintillation process. So in case of a crystal, as I was talking, why crystal? So in case of a crystal, as you say, whether this dopant atom we are talking about, or this dopant atom, or this dopant atom, the surrounding around this dopant atom, wherever it is in the matrix, remains the same. So there is a term called crystal field. So the crystal field for this dopant atom is similar everywhere. So the energy level which it will occupy in the forbidden gap of this material will remain same in this area, in this area, and in this area. So the outcoming photon, the emission photon, will always have the same energy. And that's why we will get linearity and same output. So that is why a single crystal is important. The second reason why single crystal is important is that whenever a photon is coming out, so it has to be transparent to its luminescence. When if you are talking about a ceramic material, like even aluminium oxide, so it is a ceramic material generally. if it is giving out some luminescence and it is polycrystalline, it is not transparent, then that luminescence, you cannot detect that photon which has come out. It will get scattered inside. So that's why it has to be transparent to its own luminescence, so that the light collection is from the bulb. That's why we require single crystal, because single crystals are transparent. And then absence of grain boundary, so the whatever light is there, there is no scattering, so light loss is not there. And the uniform crystal field across activator ion, which I was talking about, so we get a proper photo peak. So photo peak means whatever photoelectric effect is there, so the same energy is coming out. So we can find out the energy of the incoming gamma also. And better material property, radiation hardness is there, and then high efficiency, compact size is there. But but in this presentation I will show you that how in the emerging materials we have shown that how this we can also do the same thing without using single crystal. So first I will just give you a glimpse of single crystal growth. So single crystal growth is one technique I am showing you, is the Bridgman technique. So what happens in the Bridgman technique? This is a furnace. This is a furnace, and it has got two zones. Yellow is the high temperature zone, and this orange is the low temperature zone. So you see this something is coming down. Something has come down. So I'll go back and again come and show you what is happening. Okay. So now see. This is the crucible. So like I am growing cesium iodide. So I put the cesium iodide material inside this crucible, and then this crucible is sealed. So and this crucible is made up of quartz. Quartz, why? Because it is inert, basically inert, and the melting point of cesium iodide is around 640, and we can use a crucible of quartz till 1000 degree. But if you have to grow a material with a very high melting point, then you have to use some metal crucible like platinum or molybdenum or tantalum, like this. And as I was telling you, this furnace is a two-zone furnace. So this part is at a higher temperature. You can see here I have plotted the temperature versus this is the temperature and this is the distance. So this distance, okay. So this distance. So till this part the temperature is here at this middle point. The temperature is the melting point of the material. So like 640 degrees centigrade. And this here we keep it the temperature around 700, and here the temperature is around 600. So I have got two zones. This is at 700, this is at 600, and in between somewhere the temperature will be because of the differential 640, which is the melting point. Now this crucible was at the top. So here when it was in the top portion, it was in the melt. Totally the full material was melted because the temperature was at a higher temperature than the melting point. And now we are slowly lowering the crucible. And this lowering rate is very slow, like 1 mm per hour or 2 mm per hour. So in this distance, when initially the whole material is melted, and then when it is coming down, what happens? If you see properly, the crucible has got a very typical shape. It has got conical. So when it is coming down, so this cone is the first time which will see a temperature equal to or less than the melting point. So the solidification will start here, and then slowly it will start solidifying. So you can see here that orange color will appear. Now it has started solidifying. So like, and then it is growing. The solid part is growing. And as the crucible comes down, the full thing solidifies. So we are making a single crystal like this. The single crystal is basically phase transformation from a chaotic phase to an ordered phase. So if we can maintain this nucleation, the nucleus part which is happening first, and then we are very slowly, because the translation is very slow. So this solidification is very slow. So all the atoms which is in the melt will try to get to the same orientation as was in the nucleus, and thus this comes as a single crystal. So I will show you. So this is a furnace which I was talking about. So this is high temperature zone and this is the low temperature zone. And here through a thin wire, we hang the crucible, and this is how the crystal grows. So this is the crystal of cesium iodide doped with thallium, grown by the Bridgman process. So it is conical. So the initial nucleation starts from here and becomes so. And after cutting, so for utilization or application, we have to cut and polish. So you see the transparency. So that is how much transparency you require. So if there is any gamma falling at any part in this crystal, so it can be the light will come out, and then this you can see the transparency. So transparency is more than 80%, and the luminescence, that is the luminescence which it will give out when any gamma is coming, is around 2.5 eV, that is around 550 nanometer. So we see that all the luminescence, the material is transparent to its own luminescence. So whatever luminescence happens inside, the scintillation process happens, the photons will come out. So here you can see after processing that crystal, this is the crystal, and this is the scintillation process. Means this is a normal crystal which you can see, but when it is under any gamma, or here I have taken the photograph by shining a ultraviolet light. So under ultraviolet light also, which is also a high energy photon, it starts glowing. So it starts give out this yellowish greenish tinge. So this is the scintillation process. So this crystal is now mounted on a photomultiplier tube. And here this is the photomultiplier tube, and here is the crystal I keep. So and make this kind of, so this is our device now. And then we have to use the electronics. Maybe in your college also you have this electronics of pre-amplifier, shaping amplifier, MCA, multi-channel analyzer. So with this scintillator crystal, PM tube, and this electronics, we can detect the gamma radiation. So you can see this. So the output from this will be using the MCA, multi-channel analyzer, will give out this output. So here we see this peak, which is because of 662 keV coming from a cesium-137 radiation source. So here I have kept two radiation source. One is cesium-137, which gives out a gamma photon of energy of 662 keV, and cobalt 60, which gives out two gamma photons, one of 1.17 MeV and 1.33 MeV. So these two. So like that, using this scintillator and the electronics and PM tube, we can detect what is the radiation coming. So this is called a USB based gamma ray spectrophotometer, which we have developed in our lab. And actually we have given this instrument to many places at many and also many universities has also taken us, who has got this nuclear physics experiments going on and for their lab. So because this is a very handheld instrument and useful. So here you can see that we have used this single crystal, big single crystal for this. But when we go for X-ray radiography, like chest X-ray, so how the same material is changed, I will show you that. So X-ray radiography, in like you may have gone. So here the X-ray is coming, it is passing through the human body, and there is a screen. So it is the scintillator screen on which the radiation is falling, which generates the image. So this is done by the same cesium iodide is there. So commercially also people are using cesium iodide thallium, which we have seen in the crystal form in the earlier sites, but now it is in the form of films. It is a thin film, not exactly thin film, a thick film. But in our lab we thought that what if we do, like we are using the same crystal, we can put the same crystal and do it. So how we have done, like the same crystal, like the crystal dimension in my earlier slide was like 50 mm in diameter and 50 mm in length, that is 2-inch diameter, 2-inch length. But for a chest X-ray you need a very huge screen. So we thought we will cut and put the crystals in this fashion and do it. So, and this is the camera we made. So this crystal was there. So we have cut plates of that cesium iodide crystal like this. So here you can see under UV radiation how it starts glowing, and this is the plate which we have cut, and then we have put it in this fashion. There is 3 by 3 matrix fashion. So this radiograph is there. So this we cannot maybe use it for a medical application, but for industrial application where you want to see what is inside an instrument, like some instrument is not working, or there is some fracture in a turbine blade, or there is some rusting in some pipe. So you can use this technique. This technique is used. So like here you can see that this is the radiograph inside of a remote. This is a AC remote you can see. So which we have. So remote of an air conditioner. So difference in plastic. So this is the plastic body, and these are the PCB boards. So you can say this of different thickness, PCB tracks, etc. We can easily see. And this is a standard pattern to measure the spatial resolution of the camera. So like these are the two wires which we are very close to each other. So we can see at what distance our camera is able to focus. So we could find a resolution of 100 micron. And the same camera we have used, this is inside a multimeter. So you know you have a multimeter in your lab, so that is how it looks like inside. So these are the resistors, various resistors and jumpers are there, and some capacitors are there inside, and these are the PCB tracks, and this is the human hand. So this is there, and now we are working on like electronics, and the digital processing people are working on. So how we can remove these lines. So by that we can make a full image also. So that is how like functional material is functionalized. Next is like we have done also deposition of the cesium iodide thallium films. So the same crystal which I was talking about, now we are trying to make it into thin film. So as I told you, it melts at 640 degrees centigrade. So we have used a normal thermal evaporation system which is available in any lab, and then we have deposited the films. So this is the film structure, and if we do the cross section SEM, you can see the cesium iodide has got this property that it grows like in needle forms. So it has got this kind of needles inside it. And the property of this needle is, if there is any luminescence inside this needle is forming some because of some gamma photon or X-ray photon, so that photon will always stay within the needle. So like any gamma photon is coming and giving out of light photon here. So light photon will not pass here or here. It will stay within this needle, and then we can use a detector on this point. So that what happens, we are getting spatial resolution. Means if we are taking a photograph using that. So this is the film which we have made like that. And this is the line pair resolution we have made. So as I was telling you, what happens exactly, why we need this kind, because whatever the light X-ray is passing, sorry. So like we are detecting some, we are trying to make an image of some part of the body. So if X-rays is coming from here and here, like your hand is there and then it is passing. So whatever X-ray has come and have given the scintillation process, it should come and be collected here. Then only you can get very good spatial resolution. So this cesium iodide thin films have got this property. So we have made the thin films, and then we have seen that the line pair resolution, earlier we were saying 100 micron. So by this method, we were able to see 4 micron also. So that is an achievement in itself. And now, as I was saying about the X-ray baggage scanner, so how the same material processing the cesium iodide crystal is processed to for application in X-ray baggage scanner. So X-ray baggage scanner, you have seen this kind of thing. So here there is a X-ray machine at the top, and then you are putting your luggage on the conveyor belt. and this X-ray passes through it. But when in an X-ray baggage scanner, we cannot put this big films. No, we are putting a suitcase. So like in a chest X-ray, we have put one cesium iodide film, and we were able to detect. But we don't know in a X-ray baggage scanner how big any suitcase or any baggage will be coming. So there, what is there? They do image stitching. So what is image stitching? Basically, there is a very thin layer of cesium iodide pixels, which is there only, and then this our baggage is moving. So this layer of cesium iodide will lead to the formation of image of only one part at a time. And like for this, if we see this big suitcase, so we see the first this image is developed, then this image is taken, then this part image is taken, then this part image is taken, and then using a different softwares, the full image is stitched together to make this. So that is how a X-ray baggage scanner works. So for this kind of application, we have to cut the crystals and then make that kind of pixel, because here also you need spatial resolution. Spatial resolution means we have to find out exactly at what point, at what place, what image is there. So the image should have very good information about the position of different objects. So that's why the same crystal has been cut and now it is joined together. Like here we have made 16 small crystals are put together, and there is a reflective coating in between, so that whatever information we gather in this crystal should not go to this crystal, and subsequently like this. And this is the photo detector. So now we are not using a PMQ, we are using a photodiode. Silicon photodiode is there, and it is also, so there is 1:1 matching. So one is, so I have not got the photograph. So this each pixel here will be matched with that, and then we can form this kind of array for making. So our department of atomic energy is now trying to make this baggage scanner indigenously, because as in the morning also Fadnavis madam, our honorable vice chancellor, was saying that we are using so many foreign machines, and because of this lot of Indian currency is going to the foreign manufacturer, and it is time that we should make all these things at our own. So though this technology is old, but it is time that we Indians start doing this technology at our own end, and let us contribute to Atmanirbhar Bharat. So that was the plan of working on this technology. So that is how we are working on this part for making the indigenous X-ray baggage scanner. So we are working with ECIL Hyderabad for this. So our part is making the scintillator crystal and then coupling it with the photodiode, and ECIL will take care of all the image stitching and all those things. Now here everywhere I was talking, we have talked about the single crystal cesium iodide and the thin cesium iodide and pixelated cesium iodide. Now I am talking about polycrystalline cesium iodide. So this is a transparent ceramic of pure cesium iodide disc. So in the initial slides only I said that we need a single crystal. So there it was very clear that we do not need a a polycrystalline material, because polycrystalline materials are generally not transparent. That was the first point. So here in our lab, we have tried to make transparent cesium iodide, but which is polycrystalline in nature. It is not a single crystal in nature. Why it is so? That this is the first time this work has been done anywhere. Sorry, why it is running away? Because as I told you that for growth of single crystal, we require special furnaces, and it is very slow process. But if we can make some way so that a polycrystalline commercial normal powder can be made into transparent. So yes, we have tried that and we have been successful. Obviously, the transparency till now we have not achieved as it is transferred into single crystal. But this is the starting. So this is a new research which I have done in my lab. And here we have done, like, we have taken cesium iodide powder polycrystalline powder by vacuum hot pressing technique. So what is basically vacuum hot pressing is like we are pressing the polycrystalline powder at very high temperature and at high pressure. So because of high temperature and high pressure, but the temperature is not to the melting point. We are still at a very low temperature than the melting point. So melting point of cesium iodide like 640 degree. So I have done this pressing at 300 or 400 degree, and we have pressed into this compaction, and the pressure was in like 100 of pascals, 100 of megapascal. So 10 to the power 5 Pascal is 1 bar, 1 atmosphere. So I am going about megapascal, 100 of megapascal. So maybe like 10,000 bar or something like. So 10 ton load. So 10 ton or 20 ton load I am putting on this material at a 300 degree centigrade. So what happens, this, why a material is opaque? It is because of pores or something like that which is inside it, which leads to the scattering of the light. So if I can remove the pores, so that's why vacuum is also required. So vacuum is required so that all the air molecules which is trapped inside your polycrystalline powder is sucked out, and then I am putting pressure and temperature to make a solid structure. And in this solid structure we get the transparency also, but it is not single crystal, it remains polycrystalline. So it is then we have investigated it, and also then we have seen whether it can be used for X-ray radiography like earlier application. So this is the SCM image. So this is a very new, you can see we have got just published this material, this research now. So you can see this is a polycrystalline material, but it is very high density. They, all the crystallines, polycrystalline grains are touching each other. So that is why the transparency is there. And XRD, and you can see the transparency is quite less. In the single crystal we have achieved 80% transparency, but here 30-35%. But anyway, we are working on it. And this is the radiography testing. So this is very initial results which we have done. Similarly, X-ray is falling, and we have kept the scintillator plate here. And here we are able to, we have seen how much we are able to resolve. So now we have reached only up to 250 micrometer. So if you remember, in case of single crystal, we were able to go up to 100 nanometer, 100 micrometer. And in case of films, we were going up to 15. But now we are here in 250. But this is a new, and we were the first people who have been able to show that even polycrystalline material can be used in this way. And I'm sure with more research, this can be taken up like a emerging technology for functional material of the very old material, but emerging field. And now this is just before just 2-3 slides on this. So I have shown you single crystal, I have shown you thin film, I have shown you polycrystalline. So I will also show you some application of nanomaterials also in radiation imaging. So this is the material which gadolinium, gallium, aluminium, garnet, which I have showed earlier. So basically I will short form, we call it GGAG. So we have, I will also show its application for X-ray imaging in the lab scale. So what we have done, we have synthesized the GGAG nano powder by co-precipitation method by using gadolinium nitrate, cerium nitrate, gallium nitrate, aluminium nitrate. So co-precipitate this material. And then phase formation was there, and then we have to make some kind of structure. Now this is a nano powder, so we thought we have to make a screen for X-ray detection, for X-ray radiography. So we have mixed this powder with PMMA, dissolved PMMA dissolved in, and we have mixed the two solution and kept it for overnight. So we have been able to make this kind of films. So the loading percent here, GGAG and polystyrene, like I'm showing, we have done with polystyrene, we have done with PMMA, we have done with polyethylene. So a different polymer matrix we have done. So 5% loading, 10% loading, 20% loading. So, and this is under gamma, UV radiation, UV elimination. So you see that the scintillation effect is there, and transparency is also there. And this is, we have used test whether it can be used to detect the X-ray, we have put the films in front of our XRD machine. So XRD machine, the X-ray is falling here and we can see this glow is there. So this was the initial testing, that as we are increasing the loading percentage in the polystyrene film, the glow is better. And this is with a 50% loading. So we were able to make this X-ray screen with 50% loading, and these are all flexible. So it can be used to even detect flexible like things, and or it can be used for detection of chest X-ray, or some machine is there. So it can be made into very large film, which is also flexible. And this is the luminescence. So using X-ray luminescence, we have seen so different X-ray tube voltage. We have found out how is the X-ray. So this 550 nanometer it gives out, and using this we have been able to a line pair of 100 micron thickness spacing was resolved. So here you see that using nano material and a polymer composite, we have been able to do a X-ray screen with a resolution of 100 nanometers. So here you can see how this resolution is there. You can see it is able to some pattern is there. We are putting this pattern in between the film and the X-ray, and this pattern is generated on the film. So this is the X-ray film is there. So some different patterns we have seen. So this was very good work some year back, and we have got good publication also. And now we are, these were all this is around 1 inch films. So now we are trying to make it into a bigger size. And so that is there. So I have already shown this about the transparent ceramics. So this is the vacuum hot press facility we have, and this is a similar application for calcium fluoride nanoparticles, which we have done. We have made calcium fluoride nanoparticles, and this has also been used for detection of radiation, but in not like a scintillator, but as a dosimeter. So dosimeter are materials which generally traps the radiation, and you have to stimulate it to get the information about the radiation which it has absorbed. So calcium fluoride material was made by co-precipitation, and again by vacuum hot pressing we have made this transparent disc, and then we have been able to detect some doses. So this is 100 milligray. So I won't go much into it because I have already exceeded my time and you all must have been getting bored. So this is the measurement unit for doing a dosimetry. So maybe some later time I will tell you. And this is our group who is working on this. And again, thanks a lot for hearing me out. And I'm open for all your questions. Please let me know if you have got any problem. Thank you.
Thank you so much, ma'am, for sharing very informative research talk. Now the session is open for the discussion. In the chat box, we have 2 questions. Question 1 is, can these radiations be used for the detection of non-metals?
Radiation for the detection of non-metals?
Yeah.
Actually, it is. Radiation can be used for detection of anything. It can be used for human body also, or it can be used for industrial application also. So basically radiation is what? Radiation is passing through some object, and then our scintillator is used to detect it. So if your radiation is able to pass or semi-pass, or it can always be used for. So whether it is a human body or a tissue or a soft material, or like I have shown the metal patterns and all, it can be used.
Okay, ma'am. Our next question is, just a minute, ma'am. Can X-ray radiography used for tomographic images?
Yeah, actually tomography, X-ray radiography is one-dimensional, but when you are saying about CT scan, so CT scan is basically tomography, X-ray tomography. It is computed tomography of X-ray. So in CT scan, what they are doing, they are taking the X-ray from different direction, and then they are stitched together. All these different X-rays are stitched together to make from one-dimensional to a three-dimensional. So X-ray images are used for tomographic application, like in CT scanning.
Okay. Once again, thank you so much, ma'am, for joining with us on this virtual platform. I would like also thank Professor Dr. B.J. Lokande sir for well chairing this session. Now I owe her to Dr. R.M. Kore sir for coordinating the next session.
Thank you. Thanks a lot.
Kore sir, please unmute yourself. Kore sir, unmute yourself. You are not audible. Kore sir, you are not audible.
Hello?
Yeah, now it's audible.
Okay.
Please continue.
Thank you, Dr. T.H. Mujawar, for handovering the session. And now, today we are going to have the last phase of this one-day National E-Conference on Materials for Emerging Technologies. That is our valedictory session. So, after the enthusiastic lectures and oral presentations, I would like to request Dr. D.Y. Nadargi to take a conference overview of all the sessions. Over to Dr. Nadargi.
Thank you, Kore sir. Good evening, everyone. Honorable dignitaries, respected teachers, young researchers, and beloved students. What an auspicious day. It went so fast that we are already in the valedictory function. I'm here to give the overview of the conference. The day has started at 11 a.m. with the inaugural function, where convener Professor V.B. Patil sir has given the purpose and importance of the conference. We had an opportunity to listen to the chief guest, Dr. D.K. Aswal sir, Director NPL New Delhi. He has enlightened us with his deep knowledge about the research policies and measurements. He talked on his full of enthusiasm and valuable knowledge to the young researchers. In the presidential remarks, Honorable Vice Chancellor Madam, Dr. Mrinalini Fadavnis had thrown the light on the emergent materials and related technologies. Moving on to the keynote address by Professor P.S. Patil sir, Pro Vice Chancellor, Shivaji University, Kolhapur, he has also made a major impact on the researchers with his competence in the field of material science and especially in nanoscience. He has spoken on the nanotextiles, their synthesis, characterization, and properties. We are indebted to our resource persons, Professor B.R. Sangpal sir from Vishweshwaraya National Institute of Technology, VNIT Nagpur, and Dr. Shashwati Sen Madam from BARC Mumbai. From Professor Sangpal sir, he has spoken on the material mutualism concept, the design and development of flexible solid-state supercapacitors. And Dr. Shashwati Sen Madam has spoken on the emerging materials for radiation detection. Our oral speakers, they have made a special impact on their current research activities. Dr. Ramesh Datir from Jain University, Bangalore, has introduced us the greener pathways of developing nanocrystallites and nanocatalysts and their applications. Dr. Praveen Kumari Dwivedi from IIT Delhi has demonstrated her experimental investigations of the effect of heteroatom doped carbon microsphere, which supports on the stability and storage capacity of nano CO304 conversion anodes for application in lithium-ion batteries. Dr. Manik Rokhde from CIMET Hyderabad has shown the interesting futuristic semiconductors, its crystal growth and challenges. Dr. Nirav Joshi from Sahyadri College of Engineering and Management, Mangaluru and TFR Mumbai, he has given the insight to the high Q whispering gallery mode resonators for sensing applications at terahertz frequency range. Unfortunately, we could not able to catch Dr. Nagesh Bhandari from Baburauji Gholab College, Pune, who has planned to talk on tin oxide nano composites developed using epoxide assisted sol gel chemistry and their use as a high performance gas sensing material. In and all, we feel honored to listen to such an eminent personalities throughout the day through this online platform. This was all about the overview of the conference. So now I hand over to Dr. Kore sir to continue the valedictory function. Thank you.
Thank you, Dr. Kore, for the brief overview of the conference. Nadargi sir, sorry. I would like to now request our Pro Vice Chancellor sir, Dr. Devendranath Mishra, to give a valedictory address as well as announce the oral presentation winners for the today's one-day national conference. Over to Professor Dr. Devendranath Mishra sir.
Very good evening to everybody. Is it audible?
Yes, sir, it is audible.
Very
yes,
good.
sir, yes.
I'm privileged to be with you. I don't know whether all the guest speakers, the keynote address speakers are there still in the online mode, or otherwise the participants and my fellow colleagues in the department, in the School of Physical Science, and the members of IQSC. I'm very happy that within this pandemic situation, our university, that is Punyashlok Ahilya Devi Holkar Solapur University, has continuously been in touch with the academic improvements and research and development from various angles. And the School of Physical Sciences has been doing well in organizing in between with association of IQSC 2 or 3 such good events that has been done in the last year, and this time they have done a national e-conference on materials for emerging technology 2021. It's a very interesting field because we are all materialistic in real sense. In present world, there are very few people, those who will say that I don't love materials. In any form of materials have been attracting us from scientific point of view, from aesthetic point of view, from even everyday usage point of view. We are more fond of today user-friendly materials. We are more fond of today simple, usable materials, but durable, low cost, and efficient. From all angles, today's conference that has represented with several topics of the research in present time, whether it is done at IITs, whether it is at TIFR, in BARC, and in other institutes like Jain University, etc. I was totally attending all the members, those who have presented the papers, those who talked on various issues, including the Pro Vice Chancellor of Shivaji University, Dr. Patil, and from VNIT, Professor Sankpal, Saswati Sen, and everybody. It was a intellectual feast to me, so far as the subject knowledge is concerned. I may be little away from this particular field, but somehow I was observing the statements and the outcome of the research that they have presented are very interesting. For example, the sensors to be fixed in textile material. What a new concept. The sensors can sense the difficulties, or if you are passing through a gandagi place, I can say, some dirty place, the sensor may tell you, ask you to close your nose. And such type of things will be the future requirements as we are gradually developing ourselves to be more localized and more homely and work from home than going to the market or going to the public place or working at other places. In that context, we may lose our physical fitness very often, and we need some sensors to, some textiles to protect us. That's a new development in the post-pandemic situations. We are also interested to have more durable and rechargeable at low cost, such type of energy storage material, maybe better than supercapacitors. Even we are now changing the concepts that how fast things to be understood, and it can analyze, interpret, pass the message, and so many, which we had till now silicon as one of the materials. But now we are moving towards silicon carbide. Again, the use of such new products will be very, very interesting. And at the same time, we are again learning something from the nature, that is material mutualism. It's a very interesting concept, material mutualism. But whatever we are doing out of that, everything so far as these non-living materials are concerned, or these physical materials are concerned, what in the morning Dr. Aswal said, that the correct measurement is the successful parameter to develop our own skill and development. There's a very, very seasoned statement he gave. We can develop so many materials, we can produce so many new products from the existing materials or from the synthesis of new materials. However, we need their correct quality measurements. We lack in India, what he said, is the quality measurement where we compromise. We try to say, yes, I got it, but may not be 100% pure in my material, or it is challeable. So what we require is the correct measurement units, correct measurement parameters to be adhered to in all our skill development programs. Then and then only we will be able to compete in the world where, because with a simple example, there is no comparison, there is no challenge to the Swiss companies for their precisions in instrument making, including a small watch. The previous hand watch was definitely all Swiss made, no challenge. Later on, Japanese also came to make many improvements in their own products, so far as precisions of the material and quality of the materials are concerned. Even the Germans, they have established their brands. Whatever products they make, they bring to the market. They are all branded with the correct measurement parameters, and they qualify to those not for once but forever. Therefore, looking at all these things, this conference has opened new vistas, new orders, new technology to all of us. Those who are participating in this conference, they also must be observing several new dimensions to the same materials which we were using or are being used in the international scenario for several objectives. As a student of science and as well as biological science, I could not find one particular part that I feel missed is the biomaterials, which has tremendous potentials for the future technology, emerging technologies, like the proteins and the structures made in animals, in plants, in whatever. We could able to do definitely the sunlight absorbing photometers or even photovoltaic cells, whatever it is. But we are still not able to understand how the chlorophylls are arranged and how do they do photosynthesis. And they could able to derive their energy and make the new products, carbon products, what we are engaged with in our living process by using it for various forms of carbon products. but photosynthesis we could not do. Similarly, the sensors that is developed within the animal bodies, even in plant bodies, if you look at a simple tendril of a plant which goes around coiling into by to attach itself to a bigger place, bigger plant, and then gradually develop. If you look at its tensile strength, if you look at its materialistic strength, and the sense it can, even in the waving in the air, it can sense that such a distance it can get a support. Therefore, it moves towards that direction. Even if you look at the flower, sunflower, it rotates. So where that sensors are located, which material is doing these sensors? They are nothing but proteins. So protein as a material can be the future demand, because all these non-living materials or the inert materials have certain limitations, and its exposures have also other threats, other dangers to the environment. But along with the environment, the biological products, the biological materials are all degradable. They never cause any environmental pollution or environmental harm. Which material study has been missed in this conference? I could not find anybody talking on these protein structures, sensors, that is biologically active, and their capacities, their future related aspects. However, the total presentation in this particular conference with respect to the materials, whether it is textile material, whether it is a superconductor or capacitor, and sensors, silicon carbide, etc. All things have given us many new prospects in future research endeavor that we will be undertaking, and the new researchers can think their own research in those directions, and may possible to make some new discoveries, may help in producing new products, which, as I said in the beginning, that we all human beings are today interested in a new era, new area, new perception that at ease our lives should go without much difficulty. And science and technology is constantly been innovating or creating such type of new products from the existing materials with lot of mutualism in inputs to the materials, and getting new dimensions to the uses of the same products. I'm very happy, and really I thank to Dr. V.V. Patil, the director of the School of Physical Sciences and coordinator of IPSC, who could thought of about such a area, that is materials for emerging technology area, and contacting such great people like the director, National Physical Laboratory, Dr. Oswald, and Dr. Patil, and so many others to deliver their own work, and also to guide us on various aspects of the new technologies that we want to adopt in future, and the materials that we are going to use. I am also thankful to our Vice Chancellor Madam, Dr. Mriganini Fadnavis Madam, who, even if not belonging to the particular scientific field, so far as even especially in material science, but her lecture or her guidance at the inaugural address as a president of the function, inauguration function, was mind-blowing. With so much of understanding, she has spoken for such a long time about different aspects, and how economics is involved in material science study and in technology development. That also she has added more dimension to the knowledge we have, because we only talk on scientific development and materialistic developments, but she added the economic values and its commercialization, etc. into the topic. And I am really thankful to ma'am for her great guidance and great understanding of the subject itself. I am very happy, and I am told that I must announce that in this conference, different participants who presented their papers and their work, and to evaluate them, we had a committee, and at the end of the day, we could able to gather their points, and the evaluation record says there are 3 students or 3 participants, those who have been selected for being awarded. In that sense, in that series, I will be privileged to announce that the 3rd prize of this presentation of the today's program in the conference goes to Dr. Ramesh B. Datir of Jain University, Bangalore, the 3rd prize. The 2nd prize goes to Dr. Praveen Kumari Dwivedi, Indian Institute of Technology, Delhi. And the 1st prize goes to Dr. Manik Rokde, Scientific Officer, MET, Hyderabad. I congratulate all these participants as well as the winners of today's conference presentations. And I'm happy that whatever they presented, it went well to the minds of the evaluators also, as also to the participants in this conference. At the end, I again expect that whatever we have learned today, whatever has been presented today, will certainly help all of us, all the researchers and the administrators in future point of view, to make our research bent with modern dimensions, more user-friendly dimensions, and the good quality measurement to our products, so that it stands not only in our Indian context, but from international level too. I'm thankful to the organizer for giving me the opportunity to valedictory, to present the valedictory address, or to talk to you for a few minutes in this context. And I'm sure the presentation has reached to you in a proper sense. And I again, once again, congratulate all of you and thank you very much. Thanks a lot.
Thank you, Honorable Pro-Vice Chancellor, Sir, Dr. Devnath Mishra, Sir, for a very nice, informative, and enthusiastic valedictory address. As you have just mentioned that about the biomaterials point of view, I assure you that our Director, Professor V.B. Patil, Sir, and his team, we are going to organize one more international conference in near future. So we will take care of that point of view also, to make sense in a the biomaterial point of view for the emerging technologies also. And I would like to very much thankful for be present throughout the day and making the sense of a proper scientific person. And now I would like to request Professor Dr. B.J. Lokande, Sir, for the vote of thanks. Dr. Lokande, Sir.
Okay. Respected Vice Chancellor of our university, Dr. Fadnis Ma'am, Chief Guest, Dr. Devendranath Mishra Sir, Pro-Vice Chancellor, PH University, Solapur, and all my colleagues, students, friends, and researchers. I am here to put the vote of thanks for those who took the effort to materialize the National Conference on Materials for Emerging Technologies 2021, which is organized by School of Physical Sciences in collaboration with IQSC, SAIL, Punyashlok Ahilya Devi Holkar, Solapur University, Solapur. First of all, I would like to extend my sincere thanks to our Honorable Vice Chancellor, Ma'am, for encouraging us to organize the scientific event via online platform. I sincerely thanks to Dr. Devendranath Mishra Sir for sparing his valuable time with us and motivating us, the young researchers, for this event. I thanks the convener of this conference, that is Director of IQSC and School of Physical Sciences, Professor V.B. Patil, for organizing this event. Also, I thanks to Professor Gardi Sir, which is the member of IQSC cell. He being with us to arrange the conference since from morning. I thanks to the university officials for extending their constant encouragement in arranging the e-conference. Many thanks to organizing committee members, school of all departments and schools, members of IQSCs, technical and non-teaching, non-technical staff, for taking the efforts for the smooth running of this conference. Last but not least, because of whom the conference will not be successful, I thank to all the participants, young researchers and students, those who are attending this scientific event, and thanks to the speakers for accepting our invitation to share their research experience with us in this event. With these words, I take a full stop here, and with the kind permission of the President, I declare that conference is over. Thank you.
I will specifically also thank to both the monitors, both the anchors, both the comparers, those who took pain in the morning session and in the evening session. They also have done a good job, and they need
Thank
our
you, sir.
applause.
Thank you.
Yes.
Thank you, sir. Thank you.
Thank you.
Thanks a lot.
Thank you very much.
Now there is a small announcement for all the participants. All the participants should fill up the feedback form that would be provided to them through the email. After getting the feedback response from all the participants, the e-certificates will be transferred to all of them. Thank you.